Hello, everyone, and welcome to all speakers and delegates. I am your moderator for this meeting, and my name is Bindu. On behalf of Continuum Forums, it gives me a great pleasure to welcome you to our webinar workshop on Liutex and third generation of vertex identification for engineering applications, which is an integral part of Aerospace and Aeronautics World Forum. A very special thanks to our plenary speaker, Xiaokun Liu, and our chair and co-chair, Yuan Yang and Yashiking Gao, for making this workshop happen. We are very pleased to welcome you to both share and witness evidences in this field together. We hope you enjoy the webinar and your participation will lead to new ideas, collaborations, and research initiatives. And today it is the day one of the webinar, and we'll be starting with our plenary speaker, that is Xiaokun Liu, as a first talk.
Hello, everybody. I'm very glad to have this opportunity to give a presentation about our recent work on new fluid kinematics and fluid of velocity gradient tensor. Laminar CI is the imaginary part of the complex eigenvalue. This formula is given by Wang and us in 2019. Wang is the chairman of this workshop. First, we take a look about the traditional Helmholtz or Cauchy-Stokes tensor decomposition. The velocity gradient tensor can be decomposed to be A and B. A we call the strain part, which is symmetric. B we call the vorticity part, which is anti-symmetric. People usually think A is deformation, B is for rotation, but unfortunately, that's not true. So there are several problems because first, the vorticity cannot represent fluid rotation. The vorticity center tensor is really a mixture of rigid rotation and non-rotating shear. The symmetric strain rate tensor is a mixture really of the stretch and symmetric shear. Or we say diagonal part and off-diagonal part. But they are dependent on the coordinates. Therefore, the Cauchy-Stokes decomposition really is dependent on the coordinate system. Therefore, we want to set up a unique, we call principal coordinate system. And we can find the principal matrix. Note that tensor is unique, matrix is not. We need to give a principal coordinate. Then we can get the principal matrix. This principal coordinate has a z direction, is parallel to Liutex. And the other plane is orthogonal to the Liutex. So in these coordinates, we can get the principal matrix like this. Here, all we know it is Liutex. Epsilon, Cascade, eta are three shear parts. Laminar CI, laminar R are stretching part. They are real eigenvalue and real part of complex eigenvalues. If in the principal coordinates we get the principal matrix is easily to be decomposed to be three parts. Actually, there's three matrices. The first one is a rotation. The second one is stretching and compression. The third one is shear. We call it R, SC, and S. So velocity gradient tensor can be decomposed to rotation, stretching, and shear parts. But this decomposition at each point, really is each vortex point, we must go back to the originally Cartesian coordinates. Otherwise, we cannot do any kind of operation like differentiation or integration. So because we use the P rotation and Q rotation, we need to rotate back to the originally XY coordinate system. So then we get three parts. We call R tilt rotation, S tilt shear, and C tilt is shear and compression. Well, all the rotating part is easy to get. SC we can get as well, which have two parts. It depends on if you don't have Liutex, don't have vortex, don't have rotation, so this part will be zero. S is more complicated. You can see our recent paper called Liutex new fluid kinematics, published in GHD. Here we need to emphasize the vorticity should be decomposed to be R and S. R is rotation. S is non-rotating shear. That's easily be get. Also, this decomposition, it is not related to the coordinates. It's gardening invariant. Any coordinates. Vorticity should be decomposed to the Liutex and shear, what we call the vorticity or S decomposition. Look at this computational results. This is DNS for the flow transition. We pick a point from the leg of our laminar vortex. Because we can easily define it. The R is Liutex rotation. Vorticity is omega. Vorticity and Liutex, they are totally different. The vorticity pretty much contain the shear, not the Liutex. Liutex is only a small part of the vorticity. Anyway, vorticity cannot be used to represent the rotation. Same thing for other points, like helping vortex point. We also can find that the vorticity is very different from rotation. They're pretty much close to shear, non-rotating shear. Anyway, vorticity cannot be used to represent the flow rotation of vortex, especially near the boundary. We also derive what we call the UTA or in or tensor decomposition. Yeah, that means velocity gradient tensor is decomposed to the rotated and non-rotated part. Where the rotated part is Liutex, of course. And it is also easy to do in the originally X, Y, Z coordinate system. This is rotating part, this is no rotation power. But now we talk about the new fluid dynamics. First, we need to give some mathematical foundation. The theorem 1, and just say the divergence of velocity gradient tensor transpose equal to gradient of divergence of velocity. This is easy to prove. According to this, we can get the corollary 1. The velocity gradient strain symmetric, vorticity anti-symmetric, they are transferred. They transfer to each other by this formula. This is symmetric strain. This is vorticity. This is velocity gradient tensor. You see, they have relation. Of course, there's a term of divergence or velocity, but they transfer. For incompressible flow, that's very easy because the divergence of velocity is 0. Then you will see that's the strain, that's the vorticity, that's the velocity gradient tensor. They are equivalent. So you can use any one of them. So now is 3 questions. They just assume strain is symmetric and stress is proportional to strain. The Stokes assumption. Both strain and stress are symmetric. There's no rules vorticity. Our new governing equations assume stress is proportional to vorticity. Both vorticity and stress are anti-symmetric. There's no rules for symmetric strain, but actually both strain and vorticity have rules, as we show. They are equivalent. So that's originally, now it's 3 questions. You look, that's the new governing equations. Look at their difference. Their difference, the first, the original, now it's Stokes questions. Use strain, which is symmetric. But the new governing equation use the vorticity. Of course, they have some change in the divergence of velocity terms. So the negative 2/3 become 4 positive 4/3. That's the new governing equations. They use vorticity only. Therefore, we just use vorticity because this is anti-symmetric. We only have 3 terms, the omega x, omega y, and omega z. Similar to the stress. That's the original, now is 3 questions, stress. And that's the new governing equation. So the difference it is in the new governing equations, but this term only has 3 terms. I is not equal j. We don't need to use that term. But original now is 3 equations has 6 independent elements because they are symmetric. For incompressible flow, it's even simpler. So the now is original now is 3 questions. It's not that. They use strain. But the new governing equation, they use vorticity. Well, it looks similar, but the velocity gradient tensor has 9 terms. Strain, symmetric strain, has 6 terms. But the vorticity only have 3 terms, the computation cost is cut half. Okay, we already showed they're all equivalent. Then we check by computation results. First example is 2D backstep laminar flow. So the computation for originally now is 3 questions is red triangle. The pupil one, it is circle. So we can easily find it as almost the same for laminar flow. For the turbulent flow in S-stock, of course, we have to use the model. If we use the same model like this, the original one use some model is the pupil. The new governing equations is green. They're almost the same if we use same model. So the computation results prove they are almost equivalent. The conclusion is we know the velocity gradient tensor is unique, but we must define the metric. It also should be unique, but in general it's not. So we give a principal decomposition, which is unique in the principal coordinates. The principal decomposition also can be done in the original Cartesian coordinates. The stress calculated by the velocity gradient or by the symmetric strain or by the vorticity, they are equivalent. However, velocity gradient tensor has 9 elements. Symmetric strain has 6, but vorticity only has 3 because it's anti-symmetric. The new governing equations by vorticity is Gaussian invariant, simpler, and has clearly physical meaning because the off-diagonal elements are just anti-symmetric shape. So the new governing equations has vorticity, but now it's situation does not have. The vorticity can be further decomposed to rigid rotation and pure anti-symmetric shear. This may be useful for turbulent research. There is no reason, after our discussion about why we don't use the new governing equations to replace Navier-Stokes equations, especially for incompressible flow. You save half in the viscous term. That's my conclusion. That's the reason of publications. And the most recent one is new governing equations of fluid dynamics. Is published in the ARP Advances. We already published 3 professional books and over 40 SCI papers for Liutex and others. Well, that's the movie for the fluid transition. I don't think I have enough time to show that. Thank you.
Okay, thank you,
Any
Professor.
questions?
Yeah, any questions? We maybe we can only take one question as the time is over 20 minutes.
Can I?
Yes.
My name is Kazuo Matsura. Oh,
yes.
Okay.
Thank you very much for your wonderful presentation. My name is Kazuo Matsura from Ehime University. I have a question that if you subtract the new governing equation from the original classical Navier-Stokes equations, what kind of terms, residual remaining terms do you get?
Well, they're equal.
Equal.
Yeah,
Okay.
they are really they are same. Frankly, they're same. Yeah, but the results wise the same. Yeah, the good things, that's what I said. One is originally doesn't have vorticity, but we have vorticity now. That's one. Second, you know, you don't have vorticity, then you don't have anything, rotation, shear, something like that. The second, originally the gradient of velocity has 9 terms, but if we use now with Stokes equations, the 6 terms because symmetric. When you use our new equation, only 3 terms, they get same results. 3 terms because it's anti-symmetric. You don't have anything in the diagonal elements. Yeah, that's probably the advantage in the computation. 6 terms becomes 3 terms. Well, it's the same. There is no residue. You use now with 3 equations, subtract our equation 0, the 0. Yeah, but we don't need a 3. Yeah, we don't need 6. We only need 3. But in addition, that's what is it here? What is it could be further decomposed? Yeah.
In the level of discrete sense, new governing equation is convenient for is appropriate for the handling the discretization errors compared to the original Navier-Stokes equation regarding discretization error when you do the numerical simulation.
Well, this is I cannot guarantee, but be careful with that. This is Gaussian invariant. That means you can do for any coordinates. But for now with 3 questions, that's where we changed. You know, especially you use different coordinates, you have to rotate it. But this is no, because this is vorticity. What is the vector? There's a Gaussian invariant. You just find the the coordinates that give the projections. That's all. So this is Gaussian invariant. That's also convenient for for grids, for the coordinates rotation. I think, yeah. So
Okay.
for any grids.
Professor Liu,
Thank you very much.
Professor Mazura, we have to move on due to the time limit. Okay.
Thank you very much.
Okay. Thank you.
So thank you, Professor Liu. Very interesting work. And our next speaker is Kazuo Mazura. His topic is hierarchical clustering of vertical regions in transitional boundary layers. Okay, let's welcome Professor Mazura. Professor Liu, you may have to
share my screen.
Stop sharing.
Stop sharing.
Okay. Yes.
Okay.
Yeah, I'd like to share my screen. Yeah.
Okay.
Can you see my slide?
Yes. Yes. We can see. Okay, Professor Mazura, you can start your presentation.
In mute? Sorry. Okay. Sorry. Yes.
Doctor, your voice is not coming.
Excuse me. Can you hear my slide? Can you hear my slide?
No, doctor, we can't hear you.
Now we can hear you. Now we can hear you.
Whenever you share your screen, before you share your screen, there's an option to allow the computer to play sound. So stop sharing your screen and then try sharing your screen again, and then select the option to enable PC audio.
How can I choose? The sound? Oh, okay. I see. Okay. going to talk about hierarchical clustering of vertical regions in transitional boundary layers. My name is Kazuo Matsura from Ehime University. This study is a collaboration with Professor Yasuhide Fukumoto of Kyushu University, Japan. The topic of this study is to decompose and categorize the vertical regions into rational groups in order to understand the vortex dynamics and structures appearing in transitional boundary layers. In this presentation, first I'm going to talk about the research backgrounds and objectives. Then we propose a brand new hierarchical vortex clustering method and talk about the results. As a first step, we construct unidirectional clustering method. This method categorizes vertical points into unidirectional structures based on connectivity or closedness between the points. This method is very effective in understanding flows when most vortices are unidirectional. However, generally speaking, vortices are multiple oriented, so we extend the previous method to omnidirection. The clustering considered in this study is not only by Euclidean distance between the points. We categorize points based on mathematical terms defined on those points. We name it functional clustering. And finally, I will summarize my presentation. Laminar turbulent transition is a very complicated phenomenon. Here I'm showing DNS examples of natural transition and bypass transition. In natural transition of K regime, regular hairpin vortices are generated, and amalgamation of those hairpin vortices lead to turbulent boundary layers. On the other hand, in bypass transition, non-regular intermittent region of vortices are generated, and amalgamation of those regions lead to turbulent boundary layers. In industrial problems, the transition scenario is much more complicated. Here, I'm showing an example of stator-rotor interaction in a gas turbine cascade. The wakes from upstream stator impinge on the blade boundary layers, and the generation and propagation of disturbances takes place inside blade boundary layers. In order to mechanically investigate the local dynamics appearing in transitional boundary layers, I previously proposed algorithmic exploration of the dominant local dynamics of hairpin vortices. In this method, I extract interior points of a vortex based on the isurfaces of the second invariance of the velocity gradient tensor. Then I find nearly mean skeleton points, and after that I define the local neighborhood of a skeleton point. Then I decompose the right-hand side terms of the Navier-Stokes equations into non-further decomposable terms, large absolute value terms, and strong correlation terms. Then I could find reduced order representation of local dynamics for each skeleton point. This method is successful in mechanically investigating the local dynamics. However, we cannot track and investigate each vortex separately. So in this study, we develop a clustering method that can separate vortex clusters successfully and recognize them individually based on the physical connectivity among point clouds. The target flow for algorithm construction is laminar turbulent transition of K regime under Mach number of 0.5. Here, I'm showing the introductory target image of the present vortex clustering. In the left figure, I'm plotting the distribution of omega x streamwise vorticity on the streamwise series of x-planes. Here, we observe the discrete and continuous large omega x regions. I want to extract these vertical regions separately and analyze these regions mechanically. We call each group of vertical points superclusters and its mean curve skeleton.
In order to achieve the goal, we introduce a brand new unified hierarchical cluster members named P cluster in this study. Here, P stands for proto, sub, super, or hyper. Proto cluster or point is a vertical point. A set of points close to each other on a plane is a cluster. We get a supercluster when we stack the planar clusters in a direction. We call the mean curve of the supercluster connecting the centers of gravity as a skeleton. We get hypercluster by accumulating superclusters in time. We get skeleton time surface by tracking skeleton in time. We also consider subsets of points as subclusters. Here, I explain the unidirectional clustering. In this method, first, we extract the points belonging to the large omega x on each jth plane. We call the mesh points constituting the clusters protoclusters or points. Here, in the framework of the unidirectional clustering method, using omega x is not necessarily needed for extracting vertical points. However, when we consider, for example, streamwise structure, omega x is a good sensor for the structure, so we use omega x here. Then we evaluate correlation between each cluster on two successive jth and j+1 planes in order to connect clusters in the direction. Sometimes we encounter multiple correspondence. In that case, in order to make the cluster structure simple, upstream cluster is divided into multiple clusters, each of which has one-to-one correspondence with downstream clusters. The division of the cluster on the jth plane introduces new multiple correspondence between the j-1 and the jth plane. So we iterate the backward division process through the whole domain and finally get single correspondences over the whole domain. Here I'm showing the results of the present unidirectional clustering. Here I'm showing the supercluster element in skeletons. Superclusters and skeletons are successfully separated. Here, all skeletons of supercluster of strong vortices are shown. Skeletons with positive omega x are shown in red, and those with negative omega x are shown in blue. Here, I'm showing the distribution of omega x on the streamline series of x-planes and the skeletons of superclusters with omega x greater than some threshold. Because skeletons go through the original large omega x region, the present clustering is rational and successful. Here I'm showing the skeletons of near-wall vortices with omega x greater than some threshold. The pairing of the positive and negative skeletons are observed. I can actually construct skeleton time surfaces for this time period. The color shows the height from the wall. The previous unidirectional method is very effective when we focus on vortices with unidirectional structures. However, generally speaking, vortices are multiple oriented, so we extend the previous method to omnidirection. Two ways are considered. One is repeating x-directional clustering in y and z directions. The other is clustering based on the vortex axis. Here, I talk about repeating the x-directional clustering algorithm in the y and z directions. I take up an example of clustering a vortex ring. When we extract vertical points by unidirectional component of vorticity greater than some threshold, original points are divided into two regions in each directional method. Superclusters and skeletons are generated correspondingly. By merging superclusters or skeletons of different directions, original vortex ring is reconstructed. Although at the level of skeletons, the boundary bar appear due to boundary effect. Reconstruction is exact at the level of superclusters. In the problem of helping vortices, legs and arches can be successfully reconstructed. Here, I talk about the results of clustering based on a vortex axis. Regarding the vortex ring, exact skeleton going through the center of the vortex ring is successfully constructed. Here, I explain the method to evaluate the center of gravity required for the construction of a skeleton. A point P is projected onto the plane going through the selected point P0 and having the normal vector n. The neighboring points are similarly projected onto the plane, and the center of gravity is obtained by the average within the cluster. The present method is well applicable to the clustering of vortices in the late stage of transition as shown here. So far, we have considered clustering methods based on the connectivity by the Euclidean distance between points. We can also categorize points based on mathematical terms defined on those points. We call it functional clustering. By the functional clustering, we can categorize points based on local dynamics expressed by mathematical terms. Here, we take up a vorticity-related equation. On each point, we evaluate each of the RHS terms and get the minimum combination of the dominant mathematical terms, truly driving the RHS. By doing so, we can extract points sharing common local dynamics from different superclusters, which is beneficial in mechanically analyzing the evolution mechanism of the superclusters. Finally, I'd like to discuss the possibility of ground unification between the present hierarchical vortex clustering and Liutex. The present uni- and omnidirectional clustering methods have a large degree of freedom in extracting proto-clusters. So if we combine the present clustering method with Liutex, the emergence of more highly sophisticated methods for vortex clustering will be expected. A new hierarchical clustering method for volumetric vertical region is proposed. Point clouds in vertical regions are extracted from an instantaneous flow field using a series of planes and are grouped between consecutive planes. Cross-sectional distribution of points are then stacked in a direction. Each group of extracted points is identifiable as an individual entity that is referred to as an P cluster, with the letter P replaced by the terms proto, sub, super, and hyper according to the level of clustering. The present method is applied to the transitional boundary layer flows on a flat plate. Linkage between vertical regions, its spatial distribution, and the time variation of the vertical regions in the computational domain are successfully extracted by the proposed method. Due to the realization of the individual identification of P clusters with unique identification numbers, the algorithmic analysis of its dynamics and statistical properties is realized. Elements are clustered within each supercluster, which enables to extract subclusters having a common minimum combination of the dominant mathematical terms from different superclusters. Thank you very much.
Thank you. A very interesting topic. Any questions? Any questions for?
Thank you very much.
Okay. Any questions for Professor Mazura? Okay. Dear Professor Mazura, I have a question about the meaning or the physical meaning of the skeleton. Are they equal to the vortex axis or not?
No, it is not equivalent to the vortex center. It's only around the vortex center. It's just the nearly mean locations and not the core of the vortices. Okay. It is just representing geometrically, and it is just representing the vortices to put ID to put IDs, and it's just a representation of vortices. Yeah. Not core or not center.
So it is defined based on verticity, right?
Yes, it's just average. The averaging the points.
Okay.
In plane, XY plane, or plane normal to the the average vortices. It's just a center of gravity with the point clouds.
Okay. Thank you. Thank you. Maybe as you said, you can try to do a similar work based on Liutex vector. Maybe you can try that, and maybe the result will be interesting. Thank you.
Thank you very much.
Thank you. Okay. So we'll move on to our next talk. The next talk is Dr. Dong Jingliang. His topic is numerical detection of vortex phenomena in a patient-specific abdominal aortic aneurysm using Liutex-based method. Hello, Dr. Dong.
Hi, hi, Chair. Hi, everyone. Nice to meet you. And it's a really good opportunity to have me here. And next, I want to play my recorded presentation video. And yeah, let me share my screen.
Okay.
Oh, I'm not sure. Probably I will encounter the same problem when I play the video. I'm not sure the voice signal is also shared as well or not. Let me try.
Okay, you can see I believe Oscar Alvarez.
Can you hear it?
No, we can't hear the voice from your video.
The same thing. I'm not sure how to use this. So, I have to stop share and play it again.
Yeah, stop sharing. Okay. Maybe you will have an option on.
I found it. I found it. I'm so sorry. Share sound. Yeah.
Yeah.
Thanks for the opportunity to deliver my presentation. Today, I will talk about the numerical detection of vortex phenomena in patient-specific abdominal aortic aneurysm using Liutex-based method. In the next 15 minutes of time, my presentation will cover the research background, research challenges, and my research methods to address the identified research needs, and detailed hemodynamic results will be presented and discussed. So now please let me briefly introduce some background of this research. Abdominal aortic aneurysm, or AAA, is the dilation of the abdominal aorta due to degeneration of the arterial wall.
Yeah, sorry, Dr. Dong.
Yep.
Sorry to say this, your screen is not full. Can you just keep it in full screen mode? Because you can just click on the arrow there. Yeah, that one.
Sorry. Aorta size more than 30 millimeter, or a local dilation of abdominal aorta more than 50% of the normal vessel diameter. Epidemiological studies of AAA have shown that an increased incidence rate worldwide ranging from 4.2% to 11% per year. Despite the evolution of our understandings and treatment of AAA in the past few decades, it continues to be a major threat to health because of the grave outcome, with 80% of overall mortality in the event of rupture. So in literature, experimental and numerical approaches are widely utilized in characterize flow dynamics through AAAs and mechanical behavior of arterial tissue. Both approaches are crucial and complement each other, with offering in-depth analysis where the level of accuracy really depends on the assumptions involved in developing in the computational models and simplifications in the experimental methods. The majority of numerical approaches involved the numerical analysis using computational fluid dynamics to determine the vortex stress distribution and the flow patterns in the aneurysm region, as they can provide useful information to understand how hemodynamic loads can affect aneurysm growth and possible rupture. Despite the numerous studies that have been conducted in the past few decades, current clinical guidelines for the treatment of AAA is still primarily relying on the geometry features. So there's still no established conclusive approach for the AAA rupture risk assessment, as this problem needs to be investigated for a wide range of influential factors, such as the wall stress, wall strength, and hemodynamic analysis. As I mentioned, AAA rupture is the most catastrophic complication of the aneurysm disease that is usually accompanied by a striking overall mortality of 80%. From a biomechanical point of view, this will happen when the mechanical stress acting on the aneurysm wall exceeds the ability of the wall to withstand or hold these stresses. In addition, the disturbance of flow in the AAA is believed to contribute to the progression of the disease, which might lead to degeneration and weakening of the vessel wall. Furthermore, more than even an aneurysm is deemed as a stable vessel, the abdominal flow, the flow patterns and the recirculations developed in the aneurysm may lead to the formation of intraluminal thrombus. Therefore, there's a pressing need to obtain a comprehensive understanding of the intra-aneurysm flow fields, especially for the vortex structures in the aneurysm region. In this presentation, we developed a numerical approach to examine the flow variation in a patient-specific AAA vessel, and special efforts were spent on vortex identification by using the Liutex method. So first of all, we need to develop a digitalized arterial model. Thanks for the development of medical imaging technology, now we have the access to the arterial vessel structure by reviewing 2D CT images. With the help of many image processing software like 3D Slicer, we can segment or differentiate the arterial region from the rest of the image based on the threshold value of blood. Basically, the arterial region is brighter than the surrounding tissue. Then we can create a series of vessel lumen profiles for model reconstruction. By connecting these profiles, we can build a digitalized three-dimensional CAD model. This slide illustrates the computational mesh and boundary setup for this study. In this study, the blood flow was assumed with a mimicking fluid with a density value of 1050 and a dynamic viscosity value of 0.004 per second. Velocity inlet and pressure outlet conditions were used, and governing equations were solved by using ANSYS Fluent software. To increase the model resolution and improve simulation convergency, polyhedral mesh with 10 layers of prism layers were created, and the total element numbers after mesh independence test are 12.2 thousand. To simulate the realistic flow condition, realistic flow profiles were adopted for the present numerical model. Two phases, namely the systolic and the diastolic phases, were considered with a cardiac cycle duration of 1 second, and the time step size was set as 0.001 second to keep the current number smaller than 1. 3 time events were selected for data analysis, namely the T1, which is stand for the peak systole, and T2 stand for the early diastole, and T3 stand for the late diastole event. In this presentation, the Liutex methods was also adopted, which Liutex methods has been developed by Professor Liu's group at the University of Texas. This approach can provide a mathematical definition of the local rigid rotation part of the fluid motion, including the local rotation axis and the rotational strength. Therefore, it can provide a proper solution to represent the fluid motion regarding rotation, while the Liutex magnitude represents the twice angular speed of the swirling motion. Now let's talk about the results. This slide illustrates the velocity distributions from sagittal slices. Not surprisingly, the peak systole time event, the vessel experienced a sudden flow acceleration with a peaking velocity around 2.3 meters per second, being found as downstream of the vessel due to the relatively narrow lumen size, while the flow velocity within the aneurysm remains extremely slow due to the flow separation. For the early diastole and late diastole events, due to the significantly reduced flow rate, the velocity magnitudes also dropped significantly, with a peak velocity only around 0.5 meters per second for T2 and 0.1 meter per second for T3. These slides compare the streamlines of the blood flow at 3 time events. For time event T1, it looks that the blood flow remains mostly undisturbed except the aneurysm region, where a clockwise vortex was formed in the proximal or upper part of the aneurysm region due to the flow separation. For time events T2 and T3, the fluid is moving in an unarranged manner, or where multiple circulations were found along the vessel. Despite the vast difference between the diastole and systole phases, the presence of swirling flow motion continually remains unchanged in the aneurysm region. This slide compares the wall-shear stress distributions between all 3 time events. Our results showed the wall-shear stress in the vicinity of the aneurysm region experienced significant changes, and this type of variation is usually termed as oscillatory wall-shear stress. Research studies have revealed that oscillatory wall-shear stress played a dominant role that can affect lesion progression and the vulnerability of arterial vessel. The finding in present study confirms this flow characteristic, as the aneurysm experienced a rapid wall-shear stress variation in a cardiac cycle with a 10-fold magnitude change. Specifically, as you can see from the zoom view of the aneurysm at the peak systole event, the wall-shear stress peaks around 15 Pascal, while at the end of the cardiac cycle, the water stress rapidly drops to 1.5 Pascal. Now let's talk about the vortex structures. In this figure, isotropic surface results with a fixed Liutex magnitude of 50 were presented. As you can see, both the peak systole and the early diastole events displayed distinct vortex structures in the vicinity of the aneurysm region. And the vortex affected regions are well agreed with the streamline results, where predominant rotating flow was found as the proximal aneurysm region at T1. Later, this region was progressively expanded to occupy the whole aneurysm region at T2. Interestingly, the vortex structure almost vanished at T3, which is different from the patterns observed from the streamline results. This indicates that although conventional streamline results can confirm the presence of vortex, but its rotational strength level might be extremely low level. To provide a complete picture of the vortex magnitudes, Liutex distribution counters were extracted along the sector plane for 3 time events. From the quantified vortex results, the blood flow undergoes similar pattern changes as evidenced in literature, such as Biasetti's work, where the flow changes in the AAA vessel can be categorized into 3 phases during a typical cardiac cycle. So typical phase 1, vortices are formed in the geometrically neck region of the aneurysm, and these vortices will capture non-activated platelets, which is shown in gray dots. For phase 2, vortices reinforce and become mixed up while traveling downstream. Residence time are in the order of seconds, and high sharing at the periphery of the vortices activates platelets, which is shown in black dots. For phase 3, the vortex breaks up in the distal part of the AAA and release activated platelets, which in turn can aggregate or attach to the arterial wall. Consequently, this type of flow pattern also poses great risk of developing intraluminal thrombus. In addition to the hemodynamic results, the last type of results in this presentation is the static pressure distribution. Not surprisingly, the AAA sac region experienced a rapid force change throughout a cardiac cycle. From the peaking value around 15,400 Pascal to the lowest level around 11,400 Pascal, where a substantial pressure change of 4,000 Pascal can be observed. Now, please let me conclude this presentation. In this study, we conducted a transient numerical simulation of blood flow using a realistic AAA vessel model. Our results indicate oscillatory flow patterns can be revealed in the AAA sac region in terms of the velocity, streamlines, and watershed stress distributions. Strong swelling motions were identified by Liutex results. These structures were predominantly prevalent in the aneurysm sac region. The numerical approach presented in this study may help stratify the rupture risk of aneurysm for future studies. Thank you. That's all for my presentation. Now, thank you.
Thank you, Dr. Dong. Any questions from the audience? Actually, I have two little small questions. First, Dr. Dong, can I assume that high wall shear will certainly lead to the ache, the ache of the patient?
Based on my understanding, watershed stress doesn't cause any painful feelings It's only cause some damage to the epithelial to cause damage to the linear or inner cells of the arterial wall, which we call it epithelial cells.
Okay, interesting.
Yeah.
And my second small question is that can you do a second? Maybe you can do a second simulation, take down the aneurysm and compare the two different scenario and see what can we get from these two results?
Yeah. Let's frequently explore the simulation case scenarios in this research fields. Actually, we call it a pre and post operation comparison. Actually, we can do virtual surgery, and then we with the inputs of clinical surgeon, we can modify the arterial vessels geometry, or we can insert a stent, which is additional medical devices to change the lumen geometry. Then we compare the flow fields. Yeah, that's totally a very useful way to predict the outcome of the planned surgery. Yeah.
Okay, thank you very much. Very interesting talk.
Thank you for your question. Thanks for having me.
Thank you. If there are no other questions, any other questions? Okay, if there are no questions, thank you, Dr. Dong, and we'll have our next speaker, Yifei Yu. His topic is Galilean invariance of streamline in Vortex Liutex visualization. Let's welcome Mr. Yifei Yu. Okay.
Okay. Hello, Dr. Wang. Hello, everyone. Today my topic. Can you see my screen?
Okay, we can see you.
Oh, okay, that's good. So, today my topic is the Galilean invariance of streamline in Vortex visualization. Let's start with the concept.
You are giving us a small, small screen, not full screen.
Not full screen. It's like the presenter mode. I don't know. Maybe I share again. Well,
I think probably you are using two monitors.
Okay, so maybe I move here.
You share the wrong. Currently, you are sharing the wrong monitor. You need to share the other one.
Oh, okay. I see. Oh, yeah. Thank you. Maybe okay. Is this better?
Yeah, all good now.
Good.
Okay. So let me start from the beginning. Today my topic is Galilean invariance of streamline in Vortex Liutex visualization. Let's start with the concepts Galilean invariance and the Galilean transformation. Galilean transformation basically tells one thing, that there is a kind of transformation that tells you the relation between like the coordinator in two different systems. As long as these two systems are inertial systems, well, we know there always exists a transformation, and we call it Galilean transformation, that links the two coordinates in the two systems. Okay, and we know that the Galilean transformation can be uniquely written as the composition of a rotation, a translation, and a uniform motion of space-time. So let's look at the equation one. X prime, Y prime, Z prime represents the coordinator of something in a new reference frame, and X, Y, Z means the coordinator in the original reference frame. And they have this relation. So the new coordinator can be expressed by the rotation of the original coordinator plus the uniform motion and plus the translation. Next, we come to the Galeni invariance. Galeni invariance states that the variable is the same in all inertial frames. And we know for all inertial frames, they are linked with Galeni transformation. So in other words, the Galeni invariance means the variable keeps the same after doing Galeni transformation. And the meaning of Galeni invariance is if something is Galeni invariant, that means it has nothing to do with the choice of the coordinate systems. So this is a very good property in which you don't need to worry about the different choice of coordinate systems because in practice, well, we just randomly choose the coordinate systems. We can make sure our coordinate systems are is an inertial system, but when you communicate with somebody else, you cannot guarantee you to choose the same coordinate systems. Okay, and now next come to our topic, the vortex. Intuitively, people recognize vortex existence by the streamline banding or the pathline banding, right? So you can look at the picture. It's a common vortex street, and what our eye observe is the streamline or the path line. So when we see the path line bend or rotate, then we consider or recognize the vortex exists at that place. But this way or this intuition has some problem. So okay, so let me first show, explain the streamline Gaussian invariant. Gaussian invariant. The streamlines, well, its definition is a family of curves that instantaneously tangent to the velocity vector of the flow, and we have this relation, right? The Gaussian transformation tells us this relation, and x, y, z are the coordinator of the point. And how can we find the velocity based on the position? We just take derivative with respect to t, right? So after taking derivatives, the left column becomes u prime, v prime, v prime. Here the prime does not mean derivative, it means just the velocity in the new reference frame. Okay, and then the right, this column is UVW. Okay, and because we take derivative with respect to t, it's C1, and the last term disappear. And from the equation 3, you can see that the velocity is Gaussian invariant, right? So streamline changes if the coordinator changed. Okay, so because of this reason, it's not reliable to judge whether there is a vortex on streamline. You can see these two figures. So the left figure, the black line is the streamline. That's the streamline. And if you look at it, it's almost a straight line. And you may think there is no vortex at that position. But if you subtract the velocity at the intersection of lines, the plane, you will see the new line is a lot of curve, a lot of bend, right? So, okay, if you look at the right graph, you may think, oh, there is vortex, right? So the streamline is not reliable for vortex detection. And another example is, okay, the left graph is the right graph in figure 2, and here I just subtract the velocity by the velocity at this point, the intersection of the at this point. Then you will see the new streamline is also rotate, and you may think based on the streamline there is vortex, but you see the streamline just goes out of the idle surface, right? So well, the vortex strength is really small at that position. Okay, So okay, so what do I want to say is, well, if you change the coordinate system, right? Because I subtract the velocity of some certain terms, that means I made the new reference, and the origin of that reference is the intersection point. So if we change the reference frame, then the streamline is different, and we may get different answer from the streamline. So it's better that if we can find some quantity that is Galilean invariant and use that quantity to detect vortex. And Liutex is the Galilean invariant variable. Okay, so let's briefly introduce Liutex. Well, Liutex is a vector such that it has magnitude and has direction. And for its magnitude, we have this formula, and for the direction of Liutex, the direction is just the real eigenvector of the velocity gradient tensor, and under this condition, omega is the vorticity dot product are greater than 0. Okay, also we like explain the frame transformation. Yeah, the rotation of the coordinate velocity gradient tensor, because the direction of Liutex is related to velocity gradient tensor. So we first this is the rotation matrix. Q is the rotation matrix. So this is equation 6 is the relation of the velocity gradient tensor under a new reference systems and the velocity gradient tensor in the original reference system. Okay. Well, to show the direction is Galilean invariant. Well, we can finish that job in a very short words. So we can look at the equation 7. So we know I is the eigenvector of the velocity gradient tensor. Then we have this equation, right? The velocity gradient tensor dot product R equals to lambda R times R vector. And we know that the tensor vector, they are not dependent on the coordinator, right? So if there is no coordinator, we still have tensor and vector. So they are independent of the choice of the coordinator, right? So if you can understand in that way, you are directly get the little r, the direction of Liutex is Galilean invariant. But to make my proof rigorous, I just follow the regular process to show you that the R is Galilean invariant. Okay, we can times Q on the left of nabla V dot R vector. And here we play a trick, we times Q inverse and times Q, right? So Q inverse Q is just E, identity matrix. So we don't change anything. And we change the parentheses, we combine or we group the first 3 terms as a whole term. And from equation 6, we know Q nabla V Q inverse is just delta nabla V prime. Oh, there should be a dot. Sorry, I forgot to. Yeah, there should be a dot R. Dot R. There should be a dot R. Okay, and according to equation 7, we also times Q on the left. We have Q nabla V dot R equals to lambda R Q R, and we group these 2 terms, right? Group these 2 terms. Okay, and okay, you will find so Q nabla V R Q nabla V R. So this equals to this, right? So nabla V prime dot QR equals to lambda R Q R vector. And the equation 10 indicates QI is an eigenvector of nabla V, the velocity gradient tensor in the new reference frame if R is the eigenvector of velocity gradient tensor. Okay, and the next thing we need to show is that the Qi is the corresponding vector of R after the Galilean transformation. Because the Galilean transformation is about the point, so we used the starting point and the ending point to express the vector R. Suppose the vector R is x1, y1, z1 minus x0, y0, z0. And up during the Galilean transformation, these 2 points become these and these. So the new R prime can be expressed by x1 prime, y prime, y1 prime, z1 prime minus x0 prime, y0 prime, z0 prime. And we do the subtraction. Use the right hand side to do the subtraction, and we can factor Q out, and you will find this is just R, right? It's just R, so it's QR vector. So we have shown that the QR vector is just the R vector prime. Okay, so R prime vector is the eigenvector of the velocity gradient tensor prime. Okay, so till now the direction of Liutex is Galilean invariant. Then we talk about the magnitude of Liutex is Galilean invariant. We have this formula, right? So we can observe this formula. R is omega dot product R. So omega is vorticity. Vorticity is Galilean invariant, right? It's easy to know vorticity is Galilean invariant. And R, we just shown R is Galilean invariant, also invariant. And here, lambda Ci means the imaginary part of the complex eigenvalue. And the eigenvalue of the matrix is also Galilean invariant. So every variable in the expression is R Galilean invariant, then the R must be Galilean invariant. So the Liutex is Galilean invariant. Okay, so I just give my conclusion. Streamline is Galilean invariant, and the conclusion drawn from streamline can be misleading because of the choice of coordinates, and the Liutex Galilean invariant and does not rely on the choice of coordinator. So Liutex is a more proper way to detect vortex. Okay, thank you.
Thank you. Any questions from the audience? Any questions? Okay, we know the Galilean invariance is very important, and the streamlines are not Galilean invariant, right?
Yeah.
Very important. Okay. Okay. So Yifei talk ends our session 1, and as our plan, we will have a 10 minutes break, and then Professor Nan Gui from from Tsinghua University will host our session 2. Thank you. We'll take a break.
Okay, I think let's introduce myself. Can someone hear me? I think my camera does not work. So
yeah, we can hear you, Professor.
Yeah, I can hear you.
Yeah. So I'm sorry, my camera does not work. So I just cannot show myself on the web. So let's come to start the first session. And the first speaker is Ayush Patala. His topic is the study of vortex and the verticity in a laminar flow. Let's welcome.
Unmute. Hello everyone, can you see my screen and my sound? Can you hear my sound?
Yes, okay.
All right.
I can see.
So, okay. So first of all, thank you for having me and my greeting to the host. So my name is Ayush Patala. I'm an undergraduate student at UT Arlington. I'm currently majoring in physics and mathematics. So the title of my presentation is Study of Vortex and Verticity in a Laminar Flow. So this is a small experimental work I did with 4 other graduate students, 2 from civil engineering department and 2 from mathematics. So the outline of this talk is divided into 4 sections. First one is introduction. I'm going to give a small introduction on vortices. And the second, I'm going to talk about how the confusion between vortex and verticity arises. Like how did we end up describing vortex to the definition of verticity? And the third part is the modified superiors experiment. So this is the experiment where we're gonna show the distinguish between vortex and verticity in a rigid body rotation and in a fluid rotation. And finally, I'm gonna discuss the aspect of my presentation and the result we derived from our experiment. Okay, so vortices are ubiquitous in nature. So from kitchen sinks to galaxies, it can be found everywhere. So intuitively, when people think about vortex, they think as a swirling motion of fluid. So being significantly important in various fields such as physics, mathematics, engineering, aerospace, and all, the study of vortex, it has been studied extensively for many centuries. However, prior to the development of Liutex, we did not have an unambiguous definition of vortex. So vortex is defined in various ways, and one of the way people describe vortex is through the definition of verticity. So this definition is true for vortex in a rigid body rotation. However, for fluid rotation, we need to consider a pure shear deformation. So that's why definition of verticity is not a proper way to define vortex for both rigid body rotation and fluid rotation. However, before we talk about that, let's see how did this confusion arise in the first place. So in 19th century, Helmholtz put forward an idea of verticity tube and filament to represent the vortex in a fluid flow. So the 2 major reasons why this idea was accepted was, first of all, mathematically, it was found that the magnitude of verticity is twice the angular speed of rotation, and the direction of verticity is the sorting axis of the solid body. So over here, as you can see, let's suppose velocity is given by V, where U, V, W are 3 components of velocity, and in a similar fashion, SA represents angular speed and location vector R. So from the knowledge of kinematics, we can see that velocity equals to angular speed times location vector, and the cross product gives us the equation number 1. And one of the way verticity is defined is through as a curl of a velocity. So the gradient times the velocity gives us the result of equation 2, which shows that it is twice the angular speed. So by comparing equation 1 and equation 2, we can see verticity is twice the angular speed. So this is one of the reasons why people accepted a verticity definition to describe vortex. And the second, from the experimental verification. So a lot of previously people used to use solid verticity meter to describe the fluid detection, like to detect the fluid rotation. So this is one of the other reason why people started to accept verticity definition for to describe vortex. However, however, solid materials can only represent rigid body rotation and cannot account for fluid rotation. So in order to show this, we created a Superior's experiment where he emphasized the second point, where he used the solid verticity meter to detect fluid rotation. So let's say the three major aspects of this experiment is: one is verticity meter, second is long channel device, and third is calculating laminar flow. So I'm talking about the first one, verticity meter. So in order to distinguish between vortex and verticity, we repeated the same experiment. However, we also added our own idea to show the distinguish between vortex and verticity. So first of all, let's talk about the verticity meter that was used in our experiment. So it is a custom-made verticity meter which we 3D printed it, and there are three components of three major components. So number one is arrowhead, which gives us the direction of the rotation as the vanes turn around their axis. Second is plastic tube. So this helps the verticity meter to remain afloat. So we can also refill the water to a certain level to achieve this. And the third is vane. So the vanes are designed in right angles. So as it flows in the water, the vanes can work as a paddle wheel for the rotation. And the second aspect is the long channel device where we perform the experiment. So it is an open channel of a rectangular cross section. The channel walls are made up of clear Arctic plastic, and the frames used in this long channel device are adjustable, so the slope of the channel can be varied, like it can be changed. And the nominal dimension for this type of channel are 55, 175 to 2500 millimeters. So that's in width, height, and length. And finally, one of the major aspects of the experiment was calculating laminar flow in an open channel. So to determine if the flow is laminar or turbulent, we need to calculate the Reynolds number. So Reynolds number is given by VR by small v, where capital V represents average velocity of a flow, R represents hydraulic radius of the flow, and V is kinematic viscosity. So for kinematic viscosity, it is temperature dependent. So we can determine it by checking the lab temperature. So we got the one of the component. As for the velocity, average velocity, and the hydraulic radius of the flow, we need to do the further measurements. So let's say the velocity can be observed by calculating how much water the film was discharging at a particular time divided by the flow area. So the area can be calculated from the dimension of the device. As for the discharge, we can measure it by let's say, so the discharge is given by volume of water per time, and the volume of water, we use a beaker with a measurement over there to see how much water the channel is giving out per certain measurement. As for the time record, we just use the stopwatch. And from that, we got the velocity. And for the hydraulic radius, it is given by area divided by the weighted parameter of channel area. Like it's the same thing we got it from the dimension of the long channel device. And as for the parameter, it is given by width plus 2 times the depth of the water. And to measure the depth of the water, we use a ruler scale. And that way we got all the required components to calculate Reynolds number. So after we calculate all of these, we plug the value in our Excel sheet, and we got the Reynolds number. So for the open channel device, when the Reynolds number is less than 500, the flow stays laminar. So when we got our required number that is less than 500, we did the experiment. So for the experiment part, as the experiment setup was ready, we put the verticity meter in a laminar flow, and as expected, as expected from the previous experiment, this part is similar to that of Superior's experiment. So the verticity meter rotated as it moved in the direction of a flow. So I have a small video over here. So as you can see, the flow is going from right side to left side, and the verticity meter is rotating, and the flow over here is a laminar. There you go. And so this is the recreation of the previous experiment. And for our part, like for the very let's say for the variation, we use the dyed ink to see if the same result holds for the fluid rotation as well. So for dyed ink, here's a small video as well on the left left-hand side. So as you can see over here, and also I have also added a picture on the right side. So for the dyed ink, it just moved in a straight line without any form of rotation. Even though it's the same experiment with the laminar flow and like everything same, the Verticity Meter rotated. However, the dyed ink, it just flowed in a straight line. So what does this mean? So for discussion and conclusion, the Verticity Meter used in superiors and our first experiment was an instrument submerged in water to detect the vortices formed in the water. So however, this tool itself is rigid, so hence it will only rotate for rigid body where shear is negligible or zero. But the shear cannot be ignored in real fluid. So this means that fluid does not rotate, but the meter must rotate in a rigid body rotation. So in conclusion, vortex and verticity are two different things in fluid motion. Verticity cannot represent vortex in a fluid flow as a pure shear, there is a pure shear deformation present in the fluid, especially near the boundary layer area near the walls. So the component of verticity may be majorly shared due to RS decomposition of verticity as well. Hence, verticity does not always imply rotation. So that's the major point. So emphasizing our last point one more time. So verticity equals to vortex plus shear. For a rigid body, the shear is 0 to negligible. So for rigid body, for in case of rigid body, verticity equals to vortex. However, for a fluid rotation, there is a pure shear deformation that needs to be considered. So in a fluid motion, vortex does not equal to vortex. I'm sorry, verticity does not equal to vortex. So with that, I'd like to end my presentation. And so I'd like to thank my colleague, Oscar, Sa, Kwaji, and Yufe to help me out with this project. And I also like to thank Dr. Habib Ahamari for letting us use his lab. He's the professor from Civil Engineering Department, and our own professor, Dr. Chalkan Lee, for guiding us and giving us like different ideas during the project. So that's pretty much it. Thank you, everyone. Please let me know if you have any questions.
Okay, thank you. And anyone have question? Okay, I may ask a question. I think do you think it's possible to compute the equivalent radius by by 2 times the area of the cross area and divided by the weighted parameter?
So what was that? So to find the hydraulic radius, we can do the. I'm sorry, I didn't get your question.
In your slides, you just use a weighted you equivalent thermal hydraulic radius of your channel. I think the method to calculate the hydraulic equivalent radius, there may be coefficient that is missing in your equation.
So there is a connection problem. So let's say for our case, for the hydraulic radiation, we divided the area by the weighted parameter. So that's how we got the hydraulic radiation. So I'm pretty sure there is other way we can do calculation to get that thing, like get the radius as well.
Okay. Thank you. And let's come to the next topic. It is POD analysis on losing symmetry of flow transition with Liutex as an input vector by Buchu. Is he online? Is the second presenter here?
Well, I'm here. I'm sorry, I was on mute, so yeah, you didn't hear. Yeah. Hello, everyone. Yeah, my name is Professor Srestha. I received my PhD in this.
Please share your screen.
Oh. Okay, let me share my screen. Yeah, can you all see my screen?
Yeah, okay.
Okay. All right, so the title of my presentation is POD analysis on losing symmetry of flow transition with Liutex vector as an input method. Yeah, in this research, I have used proper orthogonal decomposition to analyze the losing of symmetry in flow transition. So let's start with what proper orthogonal decomposition is. The proper orthogonal decomposition is a technique that reduces the computational cost and time. Actually, it decomposes a vector field into a series of basis function modulated by time coefficient. Here, ux, y, zt is a vector field, so it is decomposed into several basis function multiplied by time coefficient. So we have used the SVD form of proper orthogonal decomposition. What SVD does is, like, if you have a m by n matrix A, it decomposes into three matrices, U, S, and VT, where U is an m by m orthogonal matrix, S is a singular matrix, and V is an n by n orthogonal matrix. So the singular values are arranged in the decreasing order in the singular matrix. So here we have the SVD algorithm. The first thing we need to do is we make a snapshot matrix. Snapshot matrix is nothing but a vector field that is moduled, that is sampled over a period of time. In our case, we give a Liutex vector as input in our snapshot matrix. So if this A is snapshot matrix, then we have like n column, that is like we have taken the snapshot over 100 time period, and we have like about 6.2 million Liutex vectors as input. So the dimension of our snapshot matrix is like 6.2 million times 100. So when we apply the SVD algorithm, our snapshot matrix is decomposed into three matrices, U, S, and V, where U has m by m dimension, S has m by n dimension, and V has n by n dimension. And the S is singular matrix. We have 100 singular values along the diagonal that are kept in a decreasing order. So as I told you already, U is a huge matrix which have like 6.2 million times 6.2 million dimension. So that's a huge matrix. But the good thing is that we have zeros below the singular values, right? So we can chop them off. And so the new dimension of singular matrix is n by n. And yeah, from this we can reduce the dimension of U, and that's going to be m by n. So at least it's a bit smaller. Now, this is our new form of new decomposed form of snapshot matrix. Now we can further decompose singular values. So first, let's say first our singular values actually can preserve the most of the properties of the flow. So we take R, first R singular values. That way the dimension of singular matrix is going to be R by R, and similarly the dimension of U is going to be m by R, and dimension of V is going to be R by n. So next I'm going to talk how we can get that R. So here is the formula to get that number R. So from this formula we can get R, which is the possible minimum integer, so that 100% minus the value of epsilon r is less than equal to tolerance. In my case, tolerance is approximately about 1%, that is around 0.01. So after we get R, we can write that matrix, snapshot matrix A, in the linear combination of different modes. It's nothing but the expansion of the SVD. So here we have snapshot matrix with Liutex vector as input. Here we have approximately about 6.2 million Liutex vector. And here is the figure that shows the contribution of different modes in total rotational intensity. So here we can see the first mode has about approximately 12% of the contribution. Second mode has about 11% of the contribution. Third mode has about 9%. And as we go higher, the contribution of the POD modes keep going down. So ultimately, it converges to 0. So what we can say is like the leading modes have the major contribution in total rotational strength, but when you go higher, like they have no contribution. So which means that we can remodel the fluid flow with first few modes. So here is the model structure of first few modes. So this is mode 2, this is mode 4, mode 8, and likewise I have till mode 9. So we can see as we go higher, the model structure is more like spanwise. And this is the interior view of POD modes. So this is mode 1, this is mode 2, this is mode 6, and mode 7. This also shows that as we go higher, higher modes, the vortex structure is spanwise. We can also use POD to simulate the fluid flow. Here, this is the original flow, and this is the reconstructed flow. Of course, we only took 5 modes to reconstruct the flow. So here the graph of time coefficient. This is the first mode. This is second and third mode. This is fourth and fifth mode. But here we can see as we go higher, the modes are fluctuating more. So let's talk about the losing symmetry. This is the top part, and this is the bottom part of vertex structure of flow transition. On top, at about x equals to 480, the anti-symmetry starts to begin, but on the bottom, it has already started at around 465. So this is the interior view. We can see at around 465, everything is good. We have a symmetry all over the contour, but as we go higher, like when you go to x equals to 470 and x equals to 480, I mean, when you go further to the streamwise direction, our anti-symmetry starts to kick in. So this is the interior view of that reconstructed fluid structure from first 5 modes. So here we measure the different Liutex components, and then we determine whether it is symmetric or not. So this is the definition of symmetry that I have used in my definition. Our symmetry is about y-axis. Along the y-axis, we have like 128 grids. So the line of symmetry is at j equals to 64. So this is the formula to check whether 2 points are symmetric or not. If the Liutex magnitude is approximately about the same, then they are symmetric. What I mean is, if this difference of Liutex magnitude is less than equal to 0.001, then we consider the point is symmetric. Now the question is, how do we find out that the entire contour is symmetric? For that, we calculate anti-symmetric index. Alpha I is anti-symmetric index. So NDI is a number of anti-symmetric point on the contour, and this is the sum of anti-symmetric and symmetric contour. So if when we calculate this index, if the index is less than 0.01, then this is symmetric. Right? If the index is more than 0.01, then this is anti-symmetric. This is how we determine if the contour is symmetric. So what we have found is like when we do the when we test the anti-symmetric index, we found that the anti-symmetry, we can see it hits the line from the middle first, and then the anti-symmetry starts on the bottom, and on the top, in the very late stage, the anti-symmetry kicks in. So from this work, what we have concluded is that POD actually can represent the simulation of a complex fluid flow by a simpler model with the reduced dimension. First few POD modes contribute to the maximum proportion of the rotational strength, to the rigid rotation strength. And number 3, Liutex vector can be used to determine the symmetry of vortex structure if the Liutex magnitude is same on the both sides of the line of symmetry, then those points are symmetric. And the last one, the anti-symmetry of the vortex starts from the middle, and then it goes to the bottom, and then finally it spreads to the top level. Yeah, that's it from my side. Yeah, if you guys have any question, please feel free to ask.
Okay, it's a very interesting topic. No questions? Okay, I have a question. So I don't quite sure how the POD analysis is used to compute on the. For example, in your slides, you just show the velocity fluctuation component velocity. So is it useful to use the POD analysis on the time average component velocity to show some basic structure of the time average motion of vortex?
It's actually taken over the different time period. I mean, my research is based on spatial average. I mean, it's average on position, but yeah, times are being considered.
Okay. Thank you. Now the next topic is on three-dimensional vortex structure identification of fluid coupling and analysis of spiral temporal evolution mechanism by Dr. Chai Bo-shen.
Yes, I'm here. Can you hear me?
Okay, thank you.
Yes. Hello, dear professor, scholars from all over the world. Thanks for inviting me to attend the meeting. My name is Dongyan from the School of Mechanical and Aerospace Engineering, Jilin University. I'm honored to be able to give reports at the meeting.
Dr. Jai, sorry for interrupting. I think we are not able to see your screen. I mean, I cannot see your presentation. Is that so?
Yes, please share your screen.
Oh, sorry. Hello, can you see my screen?
Okay.
Yes, now we can see that. Please start.
Thank you. Hello, dear professor, scholars from all over the world. Thank you for inviting me to attend the meeting. My name is Dongyan from School of Mechanical and Aerospace Engineering, Jilin University. I'm honored to be able to give a report at the meeting. My report topic is three-dimensional vortex structure, identification of Floyd coupling, and analysis of special temporal evolution mechanism. Due to the conflict between the tutor's course time and the meeting, this report will be carried by me instead. My grad tutor works in the School of Mechanical and Aerospace Engineering of Jilin University. His research direction is mainly divided into three parts: hydraulic component design and flow field visualization, bionic blade design and application, high-end bearing equipment testing technology. My report is mainly divided into the following three parts. The first one is research background, the second is research content, and the third is summary. The Floyd couplings are widely used in construction machinery, mining machinery, construction machinery, and other fields. There are two main types of Floyd couplings currently in use. One of them is torque limiting Floyd coupling, and the other one is speed regulating Floyd coupling. The essence of the Floyd coupling is the combination of a pop and a turbine. Figure 1 shows the principle of Floyd flow. The rotation of the blade drives the rotation of the Floyd. The rotation of the Floyd drives the rotation of the other side of the blade. Figure 2 shows the application of Floyd coupling in actual engineering. Figure 3 and 4 show the traction and the braking conditions of the Floyd coupling respectively. The internal flow mechanism of the Floyd coupling determines the extra features. Therefore, studying its internal flow is my main research work at present. Sorry. Figure 5 shows the model establishment of Floyd coupling. The extracted flow channel structure is shown in Figure 6. After the simulation analysis, not only the three-dimensional vortex structure in the flow channel can be analyzed, but also a single section can be extracted to analyze the flow states as shown in Figure 7. Two turbulence models are mainly used for the simulation analysis of the Floyd coupling. One of them is large eddy simulation, and the other one is stress blended eddy simulation. We mainly analyze its traction condition and the braking condition. Figure 8 shows the three-dimensional vortex structure in the flow channel based on the large eddy simulation model. The selection of the threshold will affect the vortex structure. Therefore, we extract the vortex structure under different thresholds, and superimpose them to show the law of change. Adopting the Q criterion requires artificial adjustment of the appropriate threshold, which requires a lot of work. The minimum threshold selected by the Omega method and the Omega Liutex method are both 0.52. We can observe the change of vortex structure under different thresholds by increasing the threshold. The result shows that the vortex structure extracted by the Omega Liutex method is more detailed. The third adjustment has little effects. The threshold adjustment has little effects on vortex structure changes. Figure 9 shows the simulation results using the SBS model. Under the same working condition, the floor channel vortex structure distribution of this method is different from the RES model. Threshold selection through artificial adjustments. Q method and the Omega method have strong similarity between the results of vortex structure extraction, but the Q method is more sensitive to threshold changes. Observing the vortex structure extracted by Omega Liutex, we can see that the applicability of this method is better for different turbulence model. Adjust the working condition to the traction working condition. Through the change analysis of the vortex structure, it can be seen that 0.52 is not the most suitable threshold under the working condition. But by analyzing the trend of the vortex structure in the floor channel, it can be known that the Omega Liutex method can capture both strong and weak vortex structure at the same time. It can be known by observing the vortex structure extracted from the SBS model. When 0.52 is selected as the threshold, the extraction effect of the vortex structure in the floor channel is not ideal. But when the threshold is increased, it can still be seen that the Omega Liutex method shows the characteristic effects on the vortex structure in the floor channel. Figure 12 shows the extraction of the vortex structure using the Omega method. Figure 13 shows the extraction of the vortex structure using the Omega Liutex method. The figures show the change of vortex structure of different cross sections when the threshold is 0.52. Analyze the changes in the vortex structure. We can observe that the effect of this method is better for the extraction of the vortex structure of the two-dimensional cross section. The basic principle is to realize the visualization of the internal flow field of the Floyd coupling based on the particle image velocity technology. Our team designed and built a test measurement system. The figure also shows the application of the test bench in the SAT-K laboratory of automobile simulation and control of Jilin University. The figure shows the flow field images of the Floyd coupling under different working conditions collected by the Floyd field visualization experiment. Through the process of image calibration, follow field parameter identification and extraction, the calculation results of the velocity field and the vorticity field are finally obtained. The comparison between the test image and the simulation result shows that the Omega Liutex method has strong applicability and does not depend on the threshold selection. Our research summary mainly has the following 3 points. Under braking condition, the simulation effect of the Omega Liutex method is the best. Under traction condition, the 0.52 threshold is not necessarily the best choice. Using the Omega Liutex method to extract two-dimensional cross sections is more effective. This study considered the influence of the internal space change of the Floyd coupling channel and the threshold adjustment on the vortex structure. Investigate the extraction effect of this method on the time evolution law of the vortex structure of the Floyd coupling channel. Thank you. The above is the content of my report. Thank you for listening.
Okay, thank you. And questions?
I have a question. Can you hear me?
Yes, I can.
I have a question. First, thanks for your impressive research work. As you have adopted 2 turbulence model in your calculation and 3 vortex identification methods. So my question is, how can you verify the vortex that is captured by the turbulence model or the vortex identification methods?
Our simulation are testing, and we will try more simulation models to identification the vortex structure for the new method.
So it is mainly captured by the method, not the turbulence model?
Yes.
Okay, thank you.
Thank you.
Okay, now the last presenter by Dr. Yan Yonghua. His title is Study of Asymmetry in Late Transitional Boundary Layer.
Yes, I'm here. Can you hear me?
Yes, okay.
Okay, let me share my screen. So can you see my shared screen?
Yeah.
Okay, thank you. Hello, everyone. My name is Yanghua Yan from Jackson State University in US. My topic is the study of the asymmetry in late transitional boundary layer. We know that the turbulence is a very common phenomenon, happens in almost everywhere, like the water flow out of a pipe, the airflow over an aircraft, and the flow inside an engine, even the larger scale, planetary flow. To study the mechanism of turbulence, we need to first study the process before the turbulence. That is called the transition flow. Although there are so many research devoted to the mechanism of turbulence formation and sustenance in the later boundary layer transition, but there are only a few research papers about the mechanisms of the chaotic flow in the later boundary layer transition. So in our study, trying to have some understanding on the mechanism of the origin of the chaotics or asymmetry, we did a direct numerical simulation of the transition flow. The code itself is well validated, and you can find the details of the code, the case setup in our previous papers. And for the mathematical model, we use the Navier-Stokes equation in curvilinear coordinates. For the numerical schemes, we use the 6th-order compact scheme in the streamwise and normal direction. And in the spanwise, we use the spectral method. The Mach number is 0.5, Reynolds number is 1000. And the numerical results are also well validated. And here it shows the graded convergence test, and also the comparison of the velocity profiles to the log law. And we also compared our numerical results with the other DNS results and with the experimental results. So for the origin of the asymmetry, the existing work leaves first DNS with the symmetric conditions will result in symmetrical results. And a small initial asymmetry disturbance grow linearly to asymmetric structures. Even very small external perturbations will significantly influence the instantaneous flow field, and that any small initial asymmetry will grow quickly and spread over the whole domain. And the initial asymmetry quantities will be enlarged at where the velocity gradient or the shear layer is very intensive. Here, to gain a deeper understanding of the mechanism of later transitional process, especially how the asymmetric perturbations influence the larger coherent structures, we conducted this DNS without any extra artificial asymmetric disturbance. That means that the numerical transition error here in our simulation is the only source of the disturbance. Of course, in the inlet, we have both 2D and 3D TS waves. And also newly developed vortex identification method Liutex is used to capture the precise vortex structures. So I think that W already gave a lot of details for the Liutex. So I will skip this detail for the Liutex here. In our simulation, start from the given 2D and 3D TS wave at the inlet, and it goes through the linear development stage, and also finally it reaches the asymmetric stage. So the domain is long enough, so we divided it into 3 parts: the tail, the middle, and the head part. Here are the numerical results of the vortex structures illustrated by Liutex in those 3 parts. We can see that complex vortex structures are already formed in the middle part. And this is the closer view, enlarged closer view of these vortex structures. Actually, we can already find the asymmetric coherent structures in the upper boundary layer. So this is a picture for the isosurface of Liutex. After around 23 periods of the TS waves, we can see obvious asymmetry structures, on the larger coherent structures here. And to study the origin of asymmetry, we calculated the asymmetry quantities of the primitive variables along the spanwise direction. In the spanwise direction, we have 2 periods of TS waves. So we just calculate, the difference, in these two waves. Of course, we calculate those quantities, the asymmetric quantities in the whole domain at every time step. These quantities actually show the same pattern. Later we will just focus on the asymmetry of the streamwise velocity. Here is U, this blue curve, since it has relatively large values. Here, the streamwise position, we can see that we'll initiate the larger values of the asymmetric quantity is at about 850. And this position is actually in the downstream part of the middle zone in our simulation, where they are already developed very complicated vortex structures. And this is the correlation table of the distribution of the asymmetries from different primitive variables. It shows that these quantities are extremely high related. So that's why we can only focus on the streamwise velocity now. Here is the animation for the evolution of the maximum of the asymmetry of the streamwise velocity. We can see that there exists some structural pattern for the generation and even evolution of this asymmetry. So the the asymmetry that is not was not generated randomly. And also here shows the profiles of asymmetry of the streamwise velocity at two different time states. We can also observe the similarity. So based on these observations, we know that the asymmetry, the generation, the initialization, the generation of the asymmetry, is not a random process. So to study the origin of asymmetry, we first investigated the asymmetry of U, the streamwise velocity with the extreme values of the velocity directives, which were considered as the major source of the asymmetry. However, as we can see here, the extreme values of the velocity directives, we have the three components. Actually, they were generated in the very beginning of the domain. So they may be not the mechanism of the generation or initiation of the asymmetry. We also got the normal locations of these extreme values of velocity directives. They are not matched either. And here we investigated the normal locations where there exists a maximum of asymmetric quantities. It can be found that the normal location of is between about 40% and 80% of the boundary layers, where there exists large coherent structures. The origin of asymmetry may be related to the generation and evolution of the coherent structures, between 40 and 80% of the boundary layer stiffness. So thus Liutex here was adopted to study the asymmetry. Since Liutex can will capture these coherent structures. Here we first compare the distribution of extreme values of Liutex and the asymmetry of the streamwise velocity. The result is same as the derivative of the velocities, not matched. Also for the normal locations, not matched well. But here, when we compare the distribution of asymmetry with the derivative of Liutex, actually, here we use the gradient of Liutex. We can see a perfect match. And also the normal locations. Also, I think that it also matched well. So for the gradient of Vertex, that means the change of the rotation in the flow. So we come to the conclusion that maybe it is related to the change of the rotation, some vortex dynamics here. So okay, and besides these 1D comparisons along the stringwise direction, we also did more strict 3D comparison. So first we choose a smaller domain, in the middle part of our our simulation. So this here it's from 700 to 900. So here in this region actually the initial of a larger asymmetric quantities was observed. And we also choose the part of domain in the middle zone where asymmetry are generated and enlarged dramatically. And a smaller region where the maximum of asymmetry was observed in the previous figures. Here, the greater cells where this relatively larger asymmetry is colored in blue, and the cells, the greater cells with a relatively larger Liutex derivative or the gradient of Liutex, they are colored in white. We can see that they match very well. So this is a enlarged view. So you can see that at the initiation stage, these two quantities really matched very well. So here is a conclusion. First, a direct numerical summation of the later stage of laminar turbulent transitional flow was conducted on a flat plate at Mach 0.5 without any extra artificial or background noises. Beginning from the asymmetric perturbation, asymmetric flow structures were still observed in the numerical results. And the newly developed vortex definition and the visualization method, Liutex, was adopted here to capture the precise position of the flow location. And it shows that the origin of the asymmetry of this transitional flow matched perfectly with the extreme Liutex gradient zone. So, since if we have a high value of Liutex gradient, that means the change of the rotation, the rotation is also very fast here. So the generation and evolution of asymmetry have a particular large correlation with the fluid rotation. Of course, we need to do more research on that, how it's related to the vortex structures in the boundary layer. The relation between the generation and evolution of asymmetry and the vortex structures will be further studied in the future. And thank you.
Okay, I think it's also a very interesting topic. Anyone have a question? Okay, I have a question. Dr. Yan, if you just run your code on the same computer, and will you get the exact same results as your first get?
I cannot say the exact same, but for the larger scales, what is structures, they will be same.
What I think you just introduced some symmetrical perturbation. So what is a symmetrical perturbation? What kind of
perturbation is from the TS waves, in the at the inlet.
Okay.
Yeah. So, in our system simulation, we don't put any asymmetric disturbance, but we still have the asymmetrical vortex structures.
Okay. Thank you. Now it is end of this session, and thank you for presenter, and thank you all the audience on the webinar. And let's have a 10 minutes break.
Well, it's like we are going to have a 20 minutes break, right?
Yeah, that's what I was looking at that too. We're about
Okay.
20 minutes
maybe we can
ahead of time.
Like have a little chatting on the topic on Liutex. So Dr. Yan, may I ask you, are you done research only on the symmetry part or the periodicity part? So it's only about the symmetry part?
Actually, I did I analyzed the data, the whole data, the total velocity.
Total velocity.
Okay. Yeah. So not just the geometry part, but for the
what I mean is that your simulation is about is two period in the spanwise direction, right?
Yes.
Two periods. Okay. So have you done any analysis on the periodicity of the data, or just symmetry part? Because symmetry and periodicity are two concepts, right?
Actually, we only focus on the asymmetry. We rerun the case in this case, but this time we don't add any perturbations.
Okay,
so we focus on the asymmetry between these two periods.
Okay. Okay.
Hello, everyone. Session 2 had ended about 20 minutes ahead of schedule, and I don't think I should start session 3 ahead of the schedule because the I only see, I think Dr. Giyu is here. He's the first speaker, but I don't think the other two are here yet. So to give them time to get here, we should wait for a bit more to get closer to the time that was scheduled for it, which is in about 15 minutes. So I'll start session 3 about 10 minutes in and to give some introductions and stuff, and then we'll go from there. Hello again, everybody. Now we've gotten down to the time, so I'll start. Thank you for joining us for session 3. My name is Charles Norwich, and I'll be the host for the session. Our first speaker will be actually the previous session host, Dr. Nan Gui, and he's from Tsinghua University in China. And we still have a little bit of time. If Dr. Nan is available right now, he could probably give a bit more information about himself.
Okay, thank you, Chairman. And the presentation will be released by me, and Gui Nan is my supervisor. And today I will make this presentation.
Okay, all right. You can share the screen whenever you.
Okay. Can you hear me and see the screen?
Yes, and I'll put it into full screen mode.
Okay.
Okay.
Okay, good evening, Chairman, ladies and gentlemen. It is my great honor for me to be here. Okay, let me take out my video.
Okay.
There may be some mistake about my video. Okay, can you see my screen?
Yes, well, you need to share the screen again. We can see you now, but you need to share the screen.
Okay, good evening, Chairman, ladies and gentlemen. It is my great honor for me to be here to share our research work with scholars home and abroad. Here is the research group from Tsinghua University, and my name is Jinsong Zhang. The topic of my presentation is about vortex field analysis of 3-dimensional bubble coalescence process based on multi-lattice Boltzmann methods and Liutex methods. Before I proceed further, first let's take a look at the overview of my presentation. I will introduce the multi-phase lattice Boltzmann method, the simulation work we conduct on the bubble coalescence, and the vortex analysis based on Liutex methods. First is my research background. As a clean and low carbon energy source, nuclear power can meet the growing demand for electricity and green gas reduction. It is a vital technology choice to realize the carbon peaking and carbon neutrality. The first generation advanced reactor of high temperature gas cooled reactor, in short for HTRPM, has significant prospects for development in terms of its inherent safety and economy. The gas liquid two-phase flow in the reactor will generate a shedding vortex, which causes fluctuation in the flow and heat transfer characteristics, and may lead to wear and tear of equipment. Therefore, the study of two-phase flow is important to ensure the operational safety of the reactor. The coalescence of droplets or bubbles is an important physical process of gas liquid two-phase flow, which has a direct impact on the number and size of the dispersed phases, and then determines the interface mass and heat transfer. The physical mechanism of the droplet or bubble coalescence is one of the key points and hotspots in the field of multi-phase flow. Okay, the second part, I will introduce the calculation method. As we know, that is Boltzmann method is a representative of describing fluid models at a mesoscopic scale. And the fluid is divided as a large number of particles with mass negative volume, which can be considered as continuous at the microscopic level and discrete at the macroscopic level. By analyzing the velocity distribution of the fluid particles, The flow information is obtained according to the moment relationship. The lattice Boltzmann method has a large potential in dealing with multi-phases and multi-scale coupled flow problems. So Boltzmann proposed the control equation describing the spatial temporal evolution law of the velocity distribution function, namely the Boltzmann equation. This equation contains the velocity distribution function of the particles and the collision operator, which portrays the interaction between microscopic fluid particles. In the previous work, the Shan-Chen pseudo-potential model is widely employed in the research, as it can automatically check the phase interface in the calculation, which is more convenient and efficient for multi-phase simulation. The pseudo-potential model introduced the Shan-Chen force for the interaction between fluid particles, and the combined force on the particles can be calculated at its surrounding location. Take a look at this equation. It contains the pseudo-potential function and the Green's function. Therefore, for a multi-component and multi-phases system consisting of n components, the lattice Boltzmann evolution equation for each component can be obtained. These items are the distribution function, the equilibrium state distribution function, the reaction time, and the external force applied to the component. Next, how do we confirm the calculation model is right? It is validated through the multi-component Poisson flow. As we can see, the left and right sides are solid wall boundaries. The center of the flow channel is occupied by liquids. The velocity distribution in the figure fits well with the theoretical formulation, whereas a certain velocity arrow at the gas-liquid interface. Therefore, the multi-phase lattice Boltzmann method is validated. Okay, the next part is about the three-dimensional bubble coalescence process simulation. The bubble coalescence process is characterized by multi-scale, nonlinear, and the strong roundedness. Therefore, the behavior and mechanism are complex. This figure displays the three-dimensional bubble coalescence process and the density distribution in the vertical central cross-section. And the time step T is the lattice unit. The bubble approach to each other for coalescence at a time step about 1,200 and forming coalescence bridge. And then this shows a horizontal expansion and stretching deformation, followed by horizontal contraction deformation. And the following is oscillation and stabilization process. So the process is completed from the time step 1,200 to 5,000. The bubbles gradually approach at the initial collision velocity, causing the continuous phase between the bubbles to form a liquid film. The bubbles are squeezed to both sides to drain the liquid, and so the liquid film sinks until it ruptures, and then the bubbles turn together and merge into one. Starting from the contact point, a coalescence bridge is formed and gradually expands at a time step about 1,600. The pressure gradient near the coalescence bridge is relatively high, and the bubble surface expands outwards into a cylindrical or ellipsoidal shape. This part of coalescence process is completed from the time step 1,200 to 2,000. And the bubble pushes the surrounding fluid outward and stretching gradually. The kinetic energy of the bubble is converted into surface energy, forming an ellipsoidal shape in the horizontal direction. Afterwards, the bubbles retracts and deforms, driven by the surface free energy, producing periodic oscillations. The amplitude decays and the energy is dissipated by the viscosity of the fluid, and then the bubble eventually stabilizes into a spherical shape. This part of coalescence process is completed from the time stat 1,200 to 5,000. And the first part is about the vortex identification, variable distribution, and the extreme value change. Okay, as the scholars mentioned above, the first generation of vortex identification is the verticity method, which is twice the average angular velocity of the fluid microelements rotation. The vortex is generally defined according to the region of the verticity concentration. The Q criterion is one of the most widely used second generation vortex identification methods. But the formula of Q contains compressed item, stretch item, and shear deformation item. So there is a certain error in judging rotating vortex. And the omega criterion, which uses the symmetry tensor and the inverse symmetry tensor based on the Cauchy-Stokes decomposition, representing the relative strength of the vortex. So it can better capture both strong and weak vortex. The third generation vortex identification method is developed as Liutex method. The method decomposes the vortex into two components, which represents the rigid rotating part and the non-rotating part, respectively. The RS decomposition provides the only tensor decomposition with Gaussian invariance. So this figure shows the spatial distribution evolution of R value during the coalescence process. When the bubble coalescence occurs at a time stat about 1,300, there is just a circular distribution of R values around the coalescence bridge. It is staggered symmetric distribution for RS and RY along the Y and X axis respectively. This is due to the expansion direction of the coalescence bridge, resulting in different rotating directions of the surrounding fluid. With the outward expansion of the bubble surface at the time stat about 2,000, the distribution area of R value is shifted from the central coalescence bridge to the interface, forming a streamlined region distribution inside the ellipsoid bubble. This part of the coalescence process is completed from the time stat 1,300 to 2,000. The bubble continues to stretch to ellipsoidal shape in the horizontal direction, and the location of the R value distribution area varies with the surface of the bubble. The upper part of the sphere showing a trapezoidal shape with narrow at the top and wide at the bottom. When the bubble retraction is close to spherical shape, the location of the R value distribution area also varies with the surface of the bubble. And the edge shape of the RS-RY distribution area shows a dumbbell shape. In addition, there also exists a R value distribution in the fluid on the outside of the bubble, indicating that the expansion of the bubble interface drives the rotation of the surrounding fluid. This part of coalescence process is completed from the time stat 4,000 to 5,000. And this figure displays the vector distribution of RS and RY and R at the central cross section. It can be seen that RS is negative along the upper side of the negative Y direction and the lower side of the Y direction. Additionally, some discrete regions of in the fluid around the bubble interface have positive and negative values of RS, characterizing the rotational intensity and direction of the fluid inside the bubble. The R value distribution exists in the region where the curvature of the bubble surface varies widely and moves along the location where the curvature varies widely as the bubble deforms. When the bubble oscillates and stabilizes, the amplitude change of the interface gradually decreases due to the kinetic energy conversion to surface energy. The rotation of the surrounding fluid decays as a result, and the amplitude of R value decreases. This part of coalescence process is completed from the time step 1,300 to 5,000. And figure 7 reveals the polar variation process of Rs, Ry, Rz, etc. in the bubble coalescence process. The discrete phase Rs and Ry obtains a single peak at the time step about 1,100, and the Rz value is smaller and obtains a peak at the time step about 1,500. While the continuous phase Rs and Ry fluctuate more and obtain peaks at different moments. Rz represents multiple peaks. In this figure, the value of R item and Q item for the discrete phase reach their extremes at the time step about 1,100. For the bubble coalescence moment, S item reaches extreme at the value at the time step about 1,100, while R and Q items reach their extreme values at different moments for the continuous phases. The former peak is near the moment of coalescence, and the latter peak is during the outward expansion of the bubble surface, representing rotation caused by the bubble exerting perturbation on the surrounding fluid. Okay, and then let's take a look at the conclusions of my presentation. The multi-phase lattice Boltzmann method is employed to calculate the two-phase three-dimensional bubble coalescence problem. And the third generation vortex identification method is adopted to identify the vortex field. Last, analyze the variation law of vortex identification variables. Firstly, the three-dimensional spatial distribution of Liutex and polar variation law is present in the process of coalescence. Secondly, it is revealed that there is a large change of interface curvature in the process of bubble coalescence. When the surrounding fluid is subjected to too much shear to resist its deformation, the fluid rotates and generates vortices, corresponding to the existence of obvious Liutex distribution apex. Thirdly, the vorticity is more seriously distributed by shear force, while Liutex is able to accurately capture and identify the vortex intensity and the rotation direction, which demonstrates outstanding advantage compared with the other vortex identification method. And the final slides are the references. So that's all about my presentation. Thank you. Thanks for listening. And following is my email address. If you have further suggestions on my research work, please feel free to contact me. And that's all. Thank you.
Thank you, Zhang. Any questions for him? No questions?
Very interesting work, Jin Song. I see you have a figure about the three-dimensional components of Liutex field, Liutex vector, right? You have the three components of Liutex field. But the shape of your flow is actually cylindrical, right? So why maybe you can use the cylindrical coordinates to show the Liutex components rather than the Cartesian components.
Okay.
Maybe
Thanks
you
for
can try that.
Suggestion.
A little suggestion. Okay.
Okay. Thank you. I will improve my slides further. Thank you.
Very interesting, and the figure is very, beautiful.
Okay. Thank you.
Any other questions for him? If there are no more questions, then we'll move along to the second speaker, which is Dr. Sarah Fahaji. She is from Deakin University, Australia, and the topic is a Liutex-based vortex identification in a realistic human nasal airway. Dr. Sarah?
Hi, everyone. Thank you so much for having me here today. I apologize that I'm speaking very loud. Family is sleeping. It's 2:14 a.m. in Australia. So yeah, it would be great to have you listen to my presentation. But as we discussed earlier, is it possible to play my video and then I take question and answer to avoid my kids wake up?
Yeah, so when you when you share your screen with the video, make sure there should be an option for you to allow the PC audio to play. So when you click share, you will see an option that says that, so you have to click that, and so when it comes up, it'll be able to play the sound.
Oh, okay. Just give me a second.
Okay, you need to share the other screen.
Okay.
Yeah, you sharing it in presentation mode. You need to share it where you can see the full screen. Are you using a second monitor?
Yes, yeah.
Yeah, so you need to share the second monitor, not the monitor that you would be looking at.
All right. Hello,
There we
everyone.
go.
I would like to present a Liutex-based vortex identification in a realistic human nasal airway. This work is in collaboration with the University of Texas at Arlington, RMIT University, and Deakin University in Australia.
The sound is very low. Did you choose the option to share the PC audio?
Range and can be easily inhaled into our respiratory airway.
You probably need to turn up your volume on your computer.
Okay. It's on 100%. Sorry. Yeah, the setting in my side is on maximum 100%. Okay. So if it didn't work, do you have my file to share on your side in case as a plan B?
Yefe, do you have a slide? Yefe? Okay. Give me 1 second. I just sent you a message with my email. You can send it to me and then I can play it.
I just sent it now.
Just give me an indication when you email to me.
I did just.
You did? Okay.
I try again now. If it didn't work, then we will wait for you to receive it.
Okay, I think I just got it. Okay. I received the email. I'm waiting for it to allow me to get the slide.
Space vortex identification in a realistic human nasal airway. This work is in collaboration between University of Texas at Arlington, RMIT University, and Deakin University in Australia. Airborne particulates are particles in submicron range and can be easily inhaled into our respiratory airway. These aerosol particles can be emitted from coal-fired power plants, motor vehicles, metal manufacturing, bushfires, mining dust, smoking, and coughing and sneezing. Exposure to aerosol particle pollution is associated with a range of respiratory and cardiovascular problems. The short-term effect on people could be eye, nose, throat, and lung irritation. It could lead into runny nose, coughing, sneezing, and shortness of breath. If a person is continuously exposed to environmental particles, it is very likely to develop some long-term consequences, including impaired lung function, asthma, chronic obstructive pulmonary disease, abbreviated as COPD, as well as increased risk of cardiovascular and heart diseases. According to WHO, more than 65 million people around the world are suffering from moderate to severe COPD. Chronic rhinosinusitis, abbreviated as CRS, impacts approximately 30 million adults in the United States every year. CRS causes an enormous impact on people's quality of life. The overall annual economic burden, direct and indirect costs of CRS in the United States was estimated to be $22 billion in 2014. Vulnerable people exposed to particulate matters are people with existing heart or lung diseases, children, elderly people, people who suffer from CRS and from COPD. Therefore, they are considered a sensitive group, which are vulnerable to airborne particles. Hence, it's very important to have a deep understanding about the inhalation exposure to airborne particles and its associated health effects. In this area, the research focus areas are inhalation exposure risks and targeted drug aerosol delivery. The underpinning knowledge is to understand the airflow dynamics and its interaction with particle transport and the deposition behaviors. There are different approaches to have a better understanding in this field, either through experiments, in vivo and in vitro experimentation, or through numerical studies through computational fluid dynamics. The previous studies are mainly focused on the interplay between the primary airflow and the airway anatomy, including the inertial impaction, gravitational sedimentation, and diffusion. Although all these studies and investigations are essential and important in developing our understanding of the physics associated with the particle deposition and the interaction between the particle and the main airway, however, the effect of secondary flow has been less studied, and the presence of vortex structures we believe would have direct impact on the deposition of the particles and would play an important role in this field. In our studies, we have reconstructed the airway model from CT images. So we used a threshold-based segmentation and identified the cavity region by lumen segmentation and reconstructed the airway cavity and exported the CAD model in STL format to be used in computational fluid dynamics studies as well as in the manufacturing process for our experimentation. In our study, we used external breathing zone to retain and capture a realistic flow pattern in the close vicinity of the nostrils. Usually, the previous studies were using an evenly distributed airflow region near the nostril, which is not capturing a realistic airflow behavior. The governing equations that are used are conservation of mass and momentum. We use a pressure inlet boundary condition at the dome for the breathing zone to apply a Dirichlet boundary condition, and then for the outlet, we extended the tube to allow the flow to be fully developed before getting into the outlet region. We use the velocity outlet to capture and control the mass that is going through the nasal airway. We also used a realistic breathing pattern and considered a full breathing cycle, which takes around 4 seconds from the start of the inhalation to the end of exhalation. In this study, we are considering the inhalation phase, and we considered 3 times during the inhalation, capturing the start of the inhalation, the peak inhalation, and just before the end of the inhalation. These times are captured at 0.1 second, 0.3 seconds, and 1.4 seconds. As it was clear from the title of our study, we are using a Liutex vortex identification. The previous studies usually used the vortices to be visualized in during the domain. However, the quantification of the vortices was not done before. The Liutex vortex identification is using a vector which can provide information about both direction and the magnitude of the vortices. The direction of the Liutex indicates the swirling axis, and the magnitude of the Liutex represents twice angular speed. In this figure, the velocity fields in a sagittal plane from the left nasal cavity is demonstrated and compared against 3 times that was illustrated in previous slides. As you can see, the flow gets accelerated after the nostril region, and then it gets developed into the nasal cavity. As expected, a higher velocity region is observed for the peak inhalation for the time of 0.3 seconds, located at the middle of the figure. However, this figure, the plane, cannot tell us all the information that we need from the flow field. A better representation of the flow field is expected. And hence, a streamline in a 3D nasal cavity model is demonstrated here. The peak velocity in all the 3 times that were selected before are demonstrated here that are happening in a similar region. Of course, the magnitude of the peak velocity is changing based on whether it's a peak inhalation or not. However, the flow structure seems to follow a similar trend in all 3 times. The wall shear stress is important in identifying the regions that the flow interacts with the wall structure, and it could play an important role in terms of the impaction and the deposition of the particles. Hence, in this figure, the wall shear stress at different times are demonstrated, and as you can see, the highest wall shear stress is observed at the peak inhalation, which reaches to as high as 3.5 pascals. The regions that are highly impacted are in the nostril region and in the middle turbulent region. In order to understand the vortex structures of the flow field inside the nasal cavity, the isosurfaces with different Liutex magnitudes of 500 and 1000 at 2 different time steps of just after the inhalation at 0.1 seconds and at the peak inhalation at 0.3 seconds are demonstrated. As you can see, similar vortex structures are being observed. However, the swirling intensity is different. The vestibule and anterior turbinate regions seem to have the highest vortex structures among the nasal cavity region. A coronal slice of the main passage is presented here, with having a Liutex magnitude as the contour plot and the streamlines overlaid on top of it. The secondary flow patterns are observed by the streamlines, and a strong swirling motion at the root of the middle meters is being observed through the contour plot. As you can see, the vortex core is located at the vicinity of the swirling region. We are expecting to have a higher deposition of the particles in the swirling region, where the swirling magnitude is much smaller and much lower compared to the vortex core, which allows the particle to have a higher residence time and interact with the wall at that location and deposit at the surface of the wall. In this figure, two images are being overlaid on top of each other. One result is obtained from transient vortex structure based on unsteady inhalation profile, and it is overlaid on our previous study for the particle deposition with constant inhalation flow rate. In order to have a better understanding of our deposition study, we will conduct another study for unsteady inhalation profile and overlay it with the vortex structure to see if the deposition locations are at the vicinity of the core of the vortices, as was anticipated. As a conclusion, a transient numerical simulation of inspirational airflow was conducted in a realistic adult nasal airway. A breathing zone was created to resolve the uneven flow distribution in the vicinity of the nostrils. Although the nasal airway underwent great velocity value and wall shear stress magnitude changes, the primary flow patterns remain relatively stable. Strong swirling motions were identified by Liutex magnitudes and were predominantly concentrated at the root of the middle meters. This may lead to enhanced particle deposition in a close vicinity to these identified vortex structures. Thank you so much for listening. I'm more than happy to take any questions.
Thank you for that presentation, Dr. Sarah. Any questions for her?
Well, Doctor, I have a small, I'm a little curious about that. It seems you did not take the hair in the nose or the nasal hair into account, right?
No, it was a smooth wall that we considered.
Okay, from my personal experience, they play a significant role, right? In healing. Okay, and very interesting work, I think. And another question relates to the the shape of the structure of the nodes. Is that obtained by your group, or it is open on the internet?
No. It is obtained by our group. So we have some CT images from actual patients. And those CT images were used. We have a database of human nasal airways now, and it's growing to help us for the further study that's going to happen, because each nasal cavity is unique and different. Even the cavities from left and right, as you know, is different from one person to another person. And in order to have a more realistic understanding of these the impact of the geometry on the nasal airflow, really we need to have a database of these nasal geometries to conduct a study and accumulate them for a more realistic understanding and unified understanding of the nasal airway. So yeah, it was done by the group.
Thank you. Thank you.
Pleasure.
Yeah, I have one question. Yeah, very interesting talk. I'm just curious. So do you have some correlation between the deposit, the particle deposit, and the Liutex? Is there coincide, overlap, or something like that?
That's a very good question. Sorry. In one of the slides, we've overlaid the particles that are being deposited based on the constant inhalation rate. However, in this study, when I visualized the Liutex vortex, it was through the unsteady or transient inhalation profile. So we are anticipating that the particles would deposit in the vicinity of the Liutex vortex core, not at the center of the core, obviously. At the center of the core, the magnitude is very high and it doesn't allow the particle to deposit. At the vicinity of the Liutex core, there is a swirling that has much smaller magnitude, and it allows the particles to have a higher residence time. They get trapped inside that swirling motion, and then they interact with the wall and deposit at those locations. So in the further study, we are expecting to see the particle deposition near the core of the vortex, the Liutex vortex.
Thank you.
Thanks.
Any more questions for her? All right, it's very interesting work you're doing, and I sort of look forward to seeing the rest of, when you do the rest of your research.
Thank you. Thank you so much. Thanks, Doctor. It was a pleasure to be here, and thank you so much for everyone's attendance. Thanks.
Now we move on to our third speaker, which is Feng Lai Kuing. Yes. They come from Shanghai Jiao Tong University in China, and their topic is analysis of vortex flows around a generic submarine based on Vertex.
Okay, I will share my screen.
Yeah.
Yes. Can you see the screen?
Yes.
Oh, okay. Okay, let me start. Good evening, everyone.
Before you begin, can you make it on full screen? You start the slideshow.
Okay. Yes.
Okay, that's good.
Okay. Good evening, everyone. It's my great honor to be here. My name is Feng Lai, and I'm a PhD student from Shanghai Jiao Tong University. Today, I would like to share my work about analysis of vortex shaped by a generic submarine based on Liutex. Sorry. Okay. This presentation is divided into 4 parts, and what we're gonna to do is analysis to generic submarine, which are now as an international benchmark. First, I would like to share the result of sub-off, and then I will share the analysis of some the dribbled BB2 submarine, and then we will draw a conclusion. And first, let's move to the introduction part. In this part, I would explain the motivation of this study. As we all know that submarine would shed a wealth of vertical structure in tower condition. As this picture shows that there are various vertical structure from the main body and appendage, such as casing, fence, rudder, and daving planes. the interaction of this coherent structure is detrimental to its hydrodynamic performance, and it's also a source of variation and emission of noise, which will have a negative impact on its steering capability. So it's pretty important to study the flow control and the vortex manipulation of submarine. Before we can do these things well, the first thing we need to do is identify vortex correctly. So here, allow me to quickly review the history of vortex identification method. The development of vortex identification can be classified into 3 generations so far. The first generation methods are based on the verticity, with the implication that the anti-symmetric part of the velocity gradient tensor obtained by Kersey-Stokes decomposition represents the rigid body rotation. However, the engineering found that it has been hard to distinguish between swelling motions and showering motions. The second generation of the vortex identification method, including Q method and lambda-2 criteria, which has been proposed to overcome the problem associated with vorticity-based method. However, the second generation methods are often plagued with case-related threshold problem in actual use and prone to contamination by sharing. So like the picture shows that with a different value of Q, we can get 2 different vortex images. Also, with a different value of lambda-2, we can get different totally completely different vortex images. So to overcome this threshold problem, Professor Chaoqun Liu proposed a new method, Liutex, which can provide a mathematical and systematical definition of the logic rigid rotation part of the fluid motion, including both the local rotation axis and the rotation strength. As the third generation of vortex identification, Liutex have 3 advantages. First, engineers do not need hesitate the value of Q. The threshold for the isosurface is always 0.52. And second, Liutex can identify vortex exclude shell motions and shell boundaries from vorticities, which will help engineers capture true vortex structure. And last but not least, Liutex can figure out the stronger and the weaker vorticities at the same time. So the objective of the present study is to analyze the vortex shape by a generic submarine and compare the result between the Liutex and the traditional Q criterion. First, I would like to show the sub-off case. And the geometry of the fully appended sub-off is shown here. And in the case of sub-off, we have compete 6 different velocity conditions with Rance method. And the Reynolds number is up to 10 million. The governing equation and turbulence model are shown here. And the computational domain and grain for the submarine are presented in this slide. A very careful design or grid topology is applied around the submarine model. The inner zone near the body, extending the height of the cell outward distance, is treated as a boundary layer refinement area, designed to capture the boundary layer and flow separation. The outer zone is used to provide a fine mesh density to resolve the flow field and offer a balance of resolution and the computational toast. The total number of the cell is about 4 million. And now we're gonna to check before we check the vortex structure, first we need to ensure that we get a correct hydrodynamic result. So we compare the resistance with the experiment. As we can see from this slide, the CFD result shows a high consistent with the experimental, which means the result we now get is reasonable. So let's check the coherent vortex structure. We compare the Q result and the Liutex result. As we can see from the picture, when we use Q criterion to identify the vortex structure, it would include shelving motions and shell boundary from vortex, which means we can see lots of fake vortex structure. When we use Liutex, it filters out many false vortex structure, and we can also see the true vortex structure like the cell horseshoe vortex. And the second example is another international benchmark, the Jubbot BB2 submarine. The geometry of the fully appendage Jubbot BB2 is showing in this slide. In this case, we compute a submarine in a real ocean environment, which is completely different from the sub-off case. Actually, stratified is a common feature for both air and ocean. We usually divided ocean into 3 layers. And also we regard the density is constant in the surface zone in the ocean and the deep layer under the ocean. However, in the cycloplan, the density change rapidly with the density due to the external environmental changes. So stratification can have a significant effect on the mixing process and the dynamics of the fluid. When submarine sails in the stably stratified environment, the internal waves and turbulence produced by the moving submarine will change the surface roughness variation on the free surface. So these characters will be detected by the radar. This motivates the present computational study of the free surface wave produced by linear stratified fluid past a submarine. So we use a totally different numerical method compared with the sub-off case. The numerical method is based on the continuity momental equation under Booth-Nash approximation, and the height equation is added to solve the NS equation. In this case, we mainly focus on the thermal clean, which means the density can be simply specified as a function of temperature. Actually, for the top 40 to 500 of the sea, meters of the sea, we can describe the density rho as a function of temperature T in the form of a linear expression. The initial density and the temperature stratification is showing here. Also, the computational domain and the grades for the submarine with free surface are presented in this slide. A half mesh with a symmetry plane y equals 0 is initially created, and it then mirrored. More cells are added in the port, starboard, rudder, and stern area to ensure we get a proper resolution of the shell layer and reduce force and momental errors. During the simulation, the Y plus is constantly kept between 30 to 100. Additionally, the refinements of the key zone like stratification and the free surface part are well maintained to guaranteeing a stable solution to capture the difference between the stratified and unstratified case. And the total number of the cell we used in this case is about 32 million. And also about the before we simulate stratified fluid, we have already verified and published some papers to ensure the accuracy and the effectiveness by calculating a spell and comparing the result with some experiment. So before we check the vortex structure as a usual procedure, we have to ensure we get a reasonable hydrodynamic result. We conduct a validation study for the homogeneous case when submarine sailing near the free surface. And it's obviously that the current method and the great strategists are able to capture free surface characteristic correctly and match the theoretical value closely. So now let's check the coherent vorticity structure. We compare the Q result and the Liutex result. The result is same as the sub-off case, as we can see from this picture. When we use Q criterion, it includes shelling motions and shell boundaries from vorticity, which means we also see some fake vortex structure. And when we use Liutex, it filters out many false vortex structure. And now we can see the true vortex structure like the cell horseshoes vortex. Okay, now let's draw a conclusion. The present work is devoted to a preliminary research on identifying vortex structure of a three-dimensional fully appended submarine at high Reynolds members. The result shows that Liutex can avoid case-related threshold used by second-generation method and capture both strong and weak vorticity at the same time. And Liutex can also offer reasonable answer for vortex definition and identification, even in the simulation of complex submarine. And last but not least, Liutex can accurately represent vortex, which will help understand the submarine's hydrodynamic performance. And the further effort will be devoted to applying to submarine maneuvering conditions and try to determine the vortex core center line by using Liutex. And okay, I finished my presentation. And thank you for your attention.
Thank you for that presentation. Does anybody have any questions for her?
I have a question. Can you hear
Go
me?
ahead. Yes, we can hear
you. First, thanks for your interesting presentation. Since your research object is a submarine and it is a large scale object, unlike a simple cylinder or a simple hydrofoil. And for example, the shedding vortex can be captured with relative depth match for a cylinder or for a hydrofoil. And my question is, to what extent and what scale of the vortex produced behind the submarine can be captured in your calculation?
Actually, how can I say that? The grid we now used actually is not so much for, around the submarine, so we can only capture some. I think it's bigger vortex structure around the submarine. Maybe the small vortex structure. When you want to catch, you need more grid around the submarine, and also the boundary layer, because the submarine has a complex shape. So when you do the mesh, you need to ensure around the submarine there are many grades, so you can get what you want. And I think in some perfect condition, when you use many grade around the submarine, you can get any vortex structure you want. Okay, thank you.
Yeah, thank you. Actually speaking, with such great number, maybe the very exact vortex structure cannot be accurately captured in your calculation. So thanks for your answer.
Thank you.
Excuse me. It's very impressive, and I just have a short question. Do you compare? Because I know you use modified Liutex omega method. Do you ever compare the method with Q criteria, and what is the difference?
When I use Liutex, I think let me see this slide. When we use Q, we can see in the top of the submarine there are some fake vortex structure because Q cannot exclude the shell in motion and shell boundary from vorticity. But when we use Liutex, the Liutex can exclude the shell in motions and shell boundary from vorticity. So when we use Liutex to see the vortex structure about submarine, this how can I say the top of the submarine, the vortex of the submarine will be more real. In my opinion, the shape of the sub-off is mature, and that means the hydrodynamic performance is good. So there will not be so much fake vortex structure at the front of the submarine. So I think the Liutex result is more reasonable, in my opinion.
Thank you.
Thank you.
Well, I'll follow Dr. Liu's question, still on this page.
Okay.
Well, we can see by Q method we can see a lot of vortex structures, right?
Yeah.
But with modified Liutex omega method, we cannot find these structures. It seems to me from the picture you showed us, that means the Q method is better, right? Have you tried the Liutex method, just the Liutex method, or
yes,
omega method with this same data?
Oh, you mean the omega method? No, I didn't try. I
what
think
about
it's
the
a
Liutex method?
good advice.
The Liutex method.
Sorry.
Have you tried the Liutex method or the Liutex vector? Have you calculated the Liutex vector?
Sorry, I only use the modified Liutex method.
Well, I believe if the Q method shows the vortex structures like this, you should get something similar to that in the wake, at least in the wake of the sub-off model, right?
Yes.
I'm a little bit curious about this results. Okay.
I think you gave me a good advice about this. I will try. What do you say? The Liutex method after the conference, and maybe in my paper I would try all the Liutex method and compare the result with Q method.
Thank you. Thank you.
Thank you.
All right. Thank you all for all the questions for her, and thank you for presenting. It is very interesting, you know, looking at the submarine and visualizing it in the mesh and everything. And unfortunately, we're out of time for if anybody else had any questions. I'm sorry, but we're closing to the end of session 3. And I want to thank all of the presenters who presented in my session. And there will be a 10-minute break, and the 4th session will be hosted by Xiangri Dong, and in about 10 minutes. Thank you.
Thank you.
Okay, hello everyone. This is Yiqian Wang from Suzhou University. Due to some personal reasons, Dr. Yuxian Xia cannot be here to host this session. So he asked me to help him out. And this is session 4, the last session of day 1. So our first speaker is Chunyang Hao from University of Shanghai for Science and Technology. His topic is study on vortex motion mechanism of a closed flow synthetic jet. So, Chunyang Hao, you can begin your presentation.
Okay. Can you hear me, my voice?
Yes, we can hear you.
Okay. Wait a moment. Okay, everyone can. Hello, everyone. My name is Chunyang Hao. I'm a postgraduate student in University of Shanghai for Science and Technology. I'm honored to be here to present my recent research. My topic is study on vortex motion mechanism of a cross-flow synthetic jet. It includes 5 parts. First of all, I will briefly introduce the research background. Secondly, I create the model and related parameters. Next, the mechanism and statistical analysis are carried out. Finally, we get some conclusions. In engineering, jet technology is widely used in various fields. Closed flow is one of the most common flow form in engineering. Synthetic jet is a new flow control technology developed in recent 20 years. It is still in the laboratory stage and has a good effect on enhancing heat transfer and releasing boundary layer separation. Compared with classical jet, the flow field structure generated by the interaction between synthetic jet and closed flow is more complex. In order to better understand and utilize vortex structure, it's necessary to study its mechanism. In order to study the mechanism, we built our 240 millimeters long and 50 millimeters wide 2-dimensional model, and opened our 5 millimeters diameter orifice 70 millimeters around the front end. The cross velocity is 20 meter per second. The orifice incidence velocity is a periodic function related to the time. The boundary condition and the related parameters are shown in the following table. In order to achieve a balance between calculation cost and calculation accuracy, therefore we choose our maximum value of 50 for grid independence. Grid setting parameters are shown in the following table. Analysis the data found that the difference between of the blue line and the red line was less than 1%. Therefore, the minimum mesh size is 0.05 millimeters, and the number of mesh is 420,000 for subsequent calculation. To observe the development and evolution of cross-flow synthetic jet, and it's necessary to understand the change of synthetic jet throughout the period. the C-stack jet can be roughly divided into 4 stages. The first stage is develop stage of the synthetic jet blow from small to large. First, a positive vortex appears on the leeward side. At this point in the quarter period, reverse vortex appears on the windward side. The vortex on the windward side is suppressed or destroyed under the action of the crossflow. And the positive vortex on the leeward side gradually develops. In the second stage, the velocity of the synthetic jet gradually decreases, and the reverse vortex on the windward side become extremely unstable, and the leeward side doesn't develop. In the third stage, the vortex on the windward side falls out under the action of the crossflow, and the positive vortex on the leeward side move downstream, and induced velocity is generated around it. Around it to induce the vortex on the windward side to accelerate and move downstream. Due to the combined action of the inhalation process of the orifice and the positive vortex on the leeward side, our new reverse is induced at the orifice. In the last stage, the vortex structure on the windward side continue to move downstream. At this time, the newly formed reverse vortex structure will be uplifted by the crossflow and move away from the wall. Meanwhile, I also use the Liutex method to identify the vortex structure in the fluid field and observe the movement of our periodic vortex of the synthetic jet. We found that using Liutex method can better identify the rotating part and the boundary of the vortex. So in the follow-up, I use the Liutex method to count the vortex scale and the average height of the vortex. Next, we made a statistics to analyze the influence of jet amplitude and frequency on the maximum vortex scale, and the average height, and the vortex rotation intensity of the fluid field. The following are the rules of my statistics. In the statistical period of different frequencies, the period was divided into 32 moments on average. The maximum vortex and average height at each moment, and the maximum vortex rotation intensity at the last moment of each period. And next is the method I proposed. The third generation of vortex in identification method, Liutex is used to identify the rotating structure of the fluid field. And the R-closed image is obtained. The image processing method is used to identify the independent vortex structure. And the maximum scale of the current time and the average height height of the vortex structure are obtained. In order to verify the feasibility of the image processing method, five independent vortex structure was selected from the fluid field, and the vortex scales obtained by image processing and tech plot integration through data compression is found that the maximum error is less than 3%. Therefore, the image method is used to statistical analysis of vortices. These are the results of our statistics. We can get some information from these figures. The first figure is the factor of amplitude and frequency on vortex scale. We can find that at the same frequency condition as the amplitude increase, the vortex scale in the fluid field gradually increases. But for f equals to 800 Hz, the effect is not significant. At the same amplitude conditions, as the frequencies increases, the vortex scale of the fluid field decreases. The second figure is the influence of amplitude and frequency on average height of vortex in the fluid field. From the overall trend, as the amplitude increases, the average height gradually increases. As the frequency increases and the average height of vortex gradually decreases. A special case occurred at f equal to 2000 Hz. From the corresponding date, it's found that the vortex is far away from the wall and in a certain range. But explain this phenomenon require further mechanistic analysis, which is what I will going to do next. The third figure is the influence of amplitude and frequency on rotation intensity. The trend is obviously with the increase of the amplitude, the rotation intensity of the vortex also increases, but the influence on the high frequency is not obvious. At the frequency increases, the rotation intensity of the vortex become small and smaller. In the end, we can get the following conclusions. The first, at the same amplitude conditions, the maximum vortex scale, average height, and the rotation intensity all tend to decreases as the frequency increases. The second, when f less than 1000 Hz, the amplitude increases has a greater impact on the rotation intensity of the vortex. When f more than 1000 Hz, the amplitude has little effect on the rotation intensity on the vortex. The third, when f equal to 1000 Hz, the average height of vortex present different trends. And the last, image processing is an effective method in statistical calculation of vortex scale and eradicate. That's the end. That's the end of my report. Thank you for listening.
May I ask a question? Please turn to page 4. Yeah, page 4. Page 6. Yeah, I'm a little puzzled. I'm not clearly understand about the sine curve. Since you can obtain such a remarkable figures representing the vortex evolution process, my question is the sine curve stands for the inlet flow in your calculation? If not, how can the vortex evolution proceed?
I don't understand your question.
My question is, what does the sine curve mean?
There.
The curve. Or can you tell me what will cause the evolution of the vortex?
Evolution.
Should explain the how the jet is ejected into the flow.
Yeah.
Okay. It is a cross flow jet, right? Cross flow. So in the spanwise direction.
Cross flow.
Okay, what is the direction of your synthetic jet? So
direct.
It's in X or Y or Z or streamwise or normal or spanwise.
And the synthetic incident angle
Okay, it has an angle, right?
Yeah.
Okay, so it's 2D simulation, right? It's 2D or 3D? It's two-dimensional.
Two-dimensional model.
Okay.
2D.
Okay, thanks
okay,
for your answer. Yeah, okay, I understand your his boundary conditions,
okay.
and now I understand the evolution process. Okay, thank you.
Okay,
thank you.
So, any other questions? Thank you, Chen Yang. So we'll move on to our next talk.
Oh, thank you.
The next speaker is Hongjie Cao. His title is Liutex force field model for complex viscous flow field of shape in restricted waters. Let's welcome Cao Hongjie. Okay, you can share your screen.
Hello everyone, it's a very great pleasure indeed for me to
Sorry, we can't hear you. The voice is very very, you know.
Hello, can everybody hear me?
Okay, it's better. It's better.
Okay.
We can hear you clearly.
First, I want to make apologize for the topic because for better suitable the topic I changed it's not focused on the Liutex force, but focus on the vortex identification. So today I would like to present my work, vortex identification method applied to complex viscous flow field of shape in restricted waters, which is instructed by Professor Wen. My presentation will cover the following aspects: introduction, numerical method, results and discussions, conclusions and prospects. First, with the development of modern shipping industry, in first structures such as ports, docks, rivers, and log chambers are increasingly difficult to meet the navigation needs of large ships. The original open channels such as the coastal, inland rivers, ports, and logs have become restricted waters. We can see from the slide here shows some common situations of the restricted waters, like the horse sitting in the log, sitting in the inland river, and sitting in the port. And just in this year, the 400-meter vessel Ever Given was stuck in the Suez Canal. More than 1 week blockage resulted in 422 vessels waiting to pass through the canal and cause huge economic losses. As a result, the issue of the restricted waters have been given more attention. In the restricted waters, the ship is in a state of low speed navigation and is vulnerable to the influence of bottom and back of the channel, which seriously threatens the navigation safety of the ship. Generally, the differences between the restricted waters and open waters can be concluded into three main aspects: the pressure distribution around the hull, the components of resistance, and the recirculation speed of water. Currently, there are many researchers have worked on the issue of restricted waters, and most of them take the Panama Lock as the researcher target. Qin Jiemeng used RANS incursions in combination with the K-omega SST turbulence model to simulate a 12,000 TEU ship model entering the third set of Panama locks. His work introduced three important instances to analyze the work, focusing on wave pattern, dynamic pressure. And my work takes a new lock as the researcher target and combines the third generation of vortex identification method to analyze the complex viscous flow field of the restricted waters. So then let me introduce the numerical method. And the whole work is on the basis of hydrodynamic solver developed by the research group. The solver is developed on the open source platform OpenFOAM, mainly composed of a dynamic overset grid module, 6 degrees of freedom module, and a numerical wave tank module. In the numerical computations, the governing inquartations are the unsteady Reynolds average Navier-Stokes inquartations, and the shear stress transport turbulence model, SSTK omega model, is selected to enclosure the unsteady RANS incursions. The SSTK omega model is one of the widely used turbulence model, which combines the advantages of the standard K epsilon and K omega model to improve the accuracy when solving the free surface and the near wall region. The dynamic overset grid technology is the key point for direct simulating the complex shipping motions. Generally, it includes 2 or more blocks of overlapping structured or unstructured grids. The free surface is captured by the volume of field approach. The relative proportion of different fields in the grid cell can be expressed as the equation where alpha represents the relative proportion. When it equals 0, it means the grid cell is completely filled with air. When it equals 1, the cell is filled with water fluid. In addition, there are 4 vortex identification methods applied to analysis the vortex field. There are first generation of vortex identification method based on the definition of verticity. The second generation method, Q criterion. The third generation method, omega R and Liutex. In the simulation model, the geometry model of an 8,000 tons ship is shown in the slide. The principal particulars are listed in the table below. In the numerical simulations, a model scale is adopted and the scale ratio is 1:29. The length between the perpendiculars of the ship model is 4.35 meters, and the speed of the ship model is 0.162 meters per second, corresponding to the Floyd number 0.023. Now let's take a brief introduction of the lock. As shown in the slide, the shape of the lock is symmetric, and at the entrance of the lock, there is an obvious rise in the bottom. In the top view, the channel changes from wide to narrow, and the water dips in the entrance of the lock has a sharp drop. The draft of the ship is 0.19 meters, while the depth of the water in the lock is only 0.276 meters. The ratio of the water depth to draft is less than 1.5. Other sides of the lock are shown in the slide. Then, in the current simulations, the grid is generated by the commercial software pointwise. The grids of the background and whole domain are generated respectively. To capture the free surface currently, a block is adopted to refine the grid near the free surface. The total grid number is about 6.41 million. The grid distribution is shown in the slide. And in this work, we regard 3 instances as the analysis targets, which represent 3 conditions of the shape in the lock. As shown in the slide, the hole enters the lock from the open water. From the time history of the drag force, when the hole moves into the lock, the water in the lock is provoked in front of the ship, which induces the increase in bow pressure and the decrease in the stern. So it causes an increase in the viscous pressure resistance. Also, an increased friction resistance will occur because of the higher velocities of the return flow. Besides, due to the shape of the lock is symmetrical and the ship enters from the middle of the lock, so the literal force is 0. The same results can be seen in the pictures of the free surface and dynamic pressure. In the photographs of the free surface, we can see the backwater phenomena obviously. The increasing blockage coefficient during a ship's entering into the lock induces an increase in the relative speed between the ship and the return flow. This causes a general reduction of the pressure. Then we use 4 vortex identification methods to analyze the vortex structures around the hole. Overall, the hole is covered fully by the vortex structure in the 3 instances identified by the first generation method. Obviously, the results are not acceptable. The Q criterion seems to more suitably capture the vortex structures in the flow field than the first generation method. As the 3rd generation vortex identification method, the omega R method is able to capture large and more vortex structures. Compared to the results obtained by the omega R method, more broken vortex structures near the hole are captured by the Liutex method. More details are shown in the follow slide. This is the time one when the ship is in the open water. And in time 2, half of the ship is in the lock. When the half of the ship enters the lock, the middle of the hull, which is also the entrance of the lock, which is also the entrance of the lock, appears 2 vortex structure. The vortex ring, the vortex ring is caused by the change of the channel, while the straight one is caused by the upward of the lock bottom. The same phenomena can be seen at the time 3. When the ship fully enters the lock, at the stern of the hull has a straight vortex structure and a large vortex. However, the Q criterion cannot capture the vortex structure well, losing much visible structures. So I changed the value of the Q. So here shows when the Q equals 1 or equals 0.5 or equals 0.2. The vortex range seems not very visible. However, when the Q equals to 0.1, the large vortex ring can be seen. When the time 4, the hull is fully entering into the lock. As shown in the slide, the vortex structure diffuses outwardly from the entrance of the lock. In the velocity field, we can also see the vortex-like structure. So here is the vortex ring, and there shows some span-wise vortex structure and a stream-wise vortex structure. So in the evolution of the vertical Liutex along the ship length direction, a vortex pair appears due to the change of the channel. And a large pair of vortex structure appears in the wake field. As the ship moves on, a vortex like common vortex streak is captured by the vertical Liutex. So finally, I would like to make a conclusion with this presentation. The numerical simulation of a towing hull in restricted waters are carried out by coupling with the overset grid technology. As the dynamic pressure of the hull and the free surface showed, the results of the CFD simulations show agreement with the experimental data. Through analysis, it found that the third generation vortex identification method can more accurately give the vortex structure around the hull. Compared with the other vortex identification methods, Liutex vector taking advantage of its directionality can be used to analyze the verticity evolution process. So further researchers will focus on the research on the hydrodynamic characters of ship propeller interaction in restricted waters. That's all my presentation. If you have any questions, I would be happy to answer it. Thank you very much.
Well, may I ask a question?
Yeah.
Well, I was greatly impressed by your research work. And the project is just like a combination of open channel flow and ship control, right? And since you conduct your research work through open form rather than commercial safety software, my question is, does the existing turbulence model will satisfy your calculation? If not, what changes do you make in the turbulence model or the VOF model? Do you make any changes in the calculation in the turbulence model?
No.
So
I just use the function and formula to process the work.
What about the VOF model?
Well,
do you make any changes?
No.
Okay, thank you.
Okay, so your vortices are in water, right? Not air, right?
Yeah.
Okay. So this in this figure, okay. Okay. Very interesting work. Any other questions?
Thank you.
Any other questions from the audience? Okay, Hongjie, thank you for your presentation. And
thank you.
we move on to our next and the last talk of day one. Xu Shun from Shanghai Jiao Tong University, China. Xu Shun, please share your screen.
Hello, can you see my screen?
Yes. Okay.
Okay. Hello, everyone. My name is Sun Xu. I'm from Shanghai Jiao Tong University, computational memory hydrodynamics lab. Today, my presentation title is Applications of Third Vortex Identification Methods for Atmospheric Boundary Layer and Turbine Wicks. The presentation can be divided into 4 parts: the background, numerical methods, results and discussions, and the conclusions. The first part, background. As a renewable resource, the wind energy has repeatedly developed in recent years. And the power capacity of wind turbine will reach up to 400 gigawatts in 2030 year. So the size of wind turbine growing repeatedly because of the prosperity for wind energy. As illustrated in the right picture, the diameter and power capacity of a wind turbine will reach up to 250 meters and 2,000 kilowatts in the future. So, with the growing of wind turbine size, the wind turbine dynamics will significantly affected by the atmospheric boundary layer turbulence inflow. Therefore, it is very necessary for us to investigate the turbine operation performance in the atmospheric boundary layer turbulence inflow. The second part, the numerical methods. In this section, the actuator line model method is used to model the wind turbine blades. As we can see, each wind turbine blade can be divided into various actuator points, and each actuator point representing the body force, including the lift and the drag. Then the body force will be added into the NS equations at source time. The right figure shows the two-dimensional inflow velocity section of the two-dimensional airfoils, where the phi is the inflow angle and beta is the local pitch angle and the alpha is the attack angle. So the body force F can be expressed as this formulation. We should note that the CL and CD are the lift and drag coefficients of the two-dimensional airfoils at each actuator point, which are from experimental date. In order to animate the numerical singularity, the regularization kernel function is used in this section, where the d represents the distance between cell center and actuator point, and epsilon denotes the control projection width. The right shows the suggestions for setup of epsilon. In this presentation, the first strategy of epsilon is adopted. As we can see, the continuity equation, the momentum equation, and the temperature transportation equation are presented. This time reflect the effects of Coriolis force due to the planetary rotation, and this time reflects the effect of temperature. Note that the temperature transportation will not be solved under the condition of neutral stability. More details about the governing equations can be found in this paper. The next part is the results and the discussions. The length, width, and the height of calculation range for the atmospheric boundary layer are 3 kilometers, 3 kilometers, and 1 kilometers respectively. 2 different wind speed and ground looseness are used for the 2 cases, and the wind direction is 240 degrees. The simulation time is long enough, such as the 18,000 seconds to obtain the quasi-equilibrium turbulence. The neutral atmospheric stability is used. For the boundary conditions, the 4 side boundaries are cyclic conditions, and the upper and lower boundaries are sleep and warm model conditions respectively. And the resolution of mesh is 8 meters, and the number is about 4 million. In this section, the NIL 5 megawatt wind turbine are used as the research object. The right table shows the wind turbine main parameters. When the wind turbine are subject to the ABR inflow, 2 mesh refine levels are adapted near the wind turbine, and the mesh resolution near the wind turbine range is 2 meters, and the total mesh number is 12 million. The simulation time for the wind turbine is 100 seconds, and the time step is 0.04. The next part is the results and the discussions. This slide shows the instantaneous velocity contours for NBL 8.0.2 case. As we can see, the velocity distribution is very complex in the ABL inflow. We can both observe the high velocity and lower velocity inflow, which reflect the necessity investigation of wind turbine subject to the ABL inflow. Those instantaneous curves are called by the Q criterion, Liutex and omega methods. As we can see, the more vortices are captured based on the Liutex method and the omega method compared with the Q criterion. And the similar conclusions can be conducted for the 240 degrees infrawind plane, where the Q criterion can only capture the vortices near the lower boundary, while the middle height vortices can be captured based on the Liutex method. And the vortices near the upper boundaries are captured using the omega method. The vortex structures are visualized by the Q and omega method. As we can see, the vortex structures in the ABL infra are very complex, and the omega method can capture the vortex structures near the upper boundary. The similar conclusions can be conducted for the lower ground looseness case. However, the difference with the previous analysis is observed. The slender vortex structures are presented using the omega method, which representing the 240 degrees infrawind direction. The reason may be that the lower ground looseness is benefit for the vortex structures maintaining its shape. Next slide is the analysis of wind turbine subject to the ABL infra. From this animation, we can see the velocity asymmetry in the turbine wake due to the turbulence infra, ABL infra, and a slender high velocity airflow is observed without considering the effect of Hubble. Besides, the wake mindering and expansion effects are also evident. And the similar conclusions are obtained from the 240 degrees infrawind plane. From those figures, we can see more vortices downstream of the rotor plane. And this phenomena is clearly observed based on the Liutex method, while the omega method can capture more vortices compared with the Q and Liutex methods. And the similar conclusions can be conducted for the 240 degrees infrawind plane. The vortex structures are visualized based on the Q criteria. As we can see, the blade tip vortex, the blade tip vortices, the Hubble vortices are observed. However, the blade tip vortex structures are quickly break up due to the high turbulence ABL infra. And the vortex structures are presented based on the Liutex method rather than the omega method because from the previous analysis, all vortices are visualized by the omega method. So it is not appropriate for us to observe the vortex structures in the wind turbine wake range. Compared with the last slide, the blade tip vortex structure boundaries and the interaction between the ambient vortices and the wake vortices and the weak expansion effects are more evident. And the same conclusions are conducted for the lower ground looseness case. The vortex structures are visualized by the Q method for the lower ground looseness case. As we can see, the clear vortex structures are visualized. However, the Shelton-like vortex structures are wrongly captured based on the Q criteria, like in this position. And this error estimate based on the Liutex method. The next part is conclusions. According to the previous analysis, we can obtain the four main conclusions. More vortex structures are identified and visualized based on the Liutex method for the ABR cases compared with the Q criterion. And the weak vortices are evident when the omega method is adopted. The vortex structures near the upper boundary are captured using the omega method, and the slender vortex structures are presented for the lower ground looseness ABR case, which is representing the 240 degrees infrawind direction. The turbine weak mindering and expansion effects are observed downstream of the two turbine rotation plane, and the high velocity wake exists at the wake center near the rotor plane without considering the effects of hub. More vortices are performed in the wind turbine wake range, and this phenomenon is well shown by the Liutex and omega methods. The blade tip vortex structure boundaries, the interaction between the ambient vortices and the turbine wake vortices and the wake expansion effect are clearly visualized based on the Liutex method. That's all about my presentation. Thank you.
Okay, thank you for a very interesting talk. Any questions? Any questions? Can you show me the last slide? The slide before your conclusion. The slide before your conclusion.
Yeah. This.
Okay, this one. Can you tell me why there are so fewer vortices in the side of your computation? Right?
Yes. Because in this presentation, the LES method is used. Here the LES simulation is used, and near the wind turbine range, the two mesh refine levels are adapted. So this method will capture the small vortices because of the high resolution of the mesh.
Okay, so you are saying that the reason is that the mesh in the away from the wind turbine is coarse, right? Coarser, right?
Yeah. Yes.
Okay, very interesting. We can see that the vortices generated by the wind turbine can sustain a substantially long range, even though the background flow is very, very turbulent, right?
Yeah.
Okay, any other questions? Okay, that ends our first day presentations, and we'll continue our workshop tomorrow. Thank you all. Thank you for listening, especially in China, Japan, and Australia. It's very late. Okay, thank you all. The first day presentations of our workshop has ended. See you tomorrow.
So thank you for your talks on the day one of the workshop, and hope you had a meaningful discussions today. And we are ending the workshop for the day one, and we'll catch up tomorrow again at 1 p.m. Frankfurt time. Bye-bye. Thank you so much.
Thank you, host. Thank you.
Thank you. Thank you.
Are you Stefan?
Yeah, I'm here on behalf of Stefan. Yeah.
Oh, yeah. Okay. Okay.
Yeah.
Thank you.
Thank you so much.
See you tomorrow.
Yeah. See you. Bye.
Bye.